Warmth, light, this is home. Over 8 billion hearts beating together in the dark. Everything we've ever known, every story, every life, exists on this tiny pale blue dot. But today we're searching for something far beyond imagination. As we leave our solar system behind and set course for Stephenson 218, Saturn drifts past us. Its rings stretch thousands of miles across, yet in places they're thinner than a city street. Ahead of us lies a journey of nearly 19,000 light years. Out here, there are no signposts, no familiar landmarks, just a vast, silent ocean between the stars. From this distance, we wouldn't even be able to find the sun unless we knew exactly where to look. Our speed is now beyond intuition. Numbers stop helping. We're racing toward one of the largest stars ever discovered. As we adjust our course, we enter the Scutum Centaurus arm of the Milky Way. This is where it lives, the giant we came to see. Let's start with something familiar. This is our sun, the source of all warmth, all life we've ever known. Now watch closely as we replace it with Stephenson 218. The sun vanishes inside it. Mercury's orbit disappears. Venus is gone. Earth, the orbit where we live and love, is swallowed whole. Mars follows. Even Jupiter and Saturn, the giants of our solar system, are completely engulfed. Stephenson 218 is more than 2,000 times larger than our sun. This is Earth, everything we are, every memory, every dream. This is our sun, the star that holds our world together, and this is Stephenson 218. At this scale, comparison stops working. Our sun doesn't orbit it, it simply disappears inside. Numbers collapse, language breaks down. This isn't just bigger, it's a different category of reality. Imagine standing on Uranus if Stephenson 218 replaced our sun. The star would dominate the sky, stretching beyond comprehension. A sunset like this would feel unreal. After that, the night sky would never feel the same again. A star like this doesn't simply shine, it overwhelms. Now picture Neptune under the same sky, beautiful, surreal, and completely alien. The horizon would be flooded with light. The very idea of what a star is would change. But this is where the illusion ends. A star like Stephenson 218 could never truly replace our sun. Its sheer size would tear the inner solar system apart. It wouldn't be part of the system. It would be the system. And yet, as overwhelming as it feels to us, this star is still just one among billions. In a universe where size shows no mercy, even giants are temporary. Stephenson 218 is burning its fuel at an extreme rate. Every second it moves closer to its own collapse. One day it will end, and the universe will continue on, without witnesses, without memory, without meaning except the meaning we choose to give it. From here, the sun is no longer a reference point, it's a memory. What we're seeing isn't just size, it's scale breaking down. Around a star like Stephenson 218, there is no balance, only dominance. Not because it's bigger than our sun, but because it's so extreme that our intuition simply can't follow. Stephenson 218, often called ST218, is an enormous star located in the constellation Scorpius. It is a red supergiant, a class of stars known for their vast size and cool surface temperatures. Its size and luminosity make it potentially the largest star ever discovered, capturing the interest of astronomers and astrophysicists worldwide. The star was initially detected through infrared observations by astronomers surveying the Milky Way. Its brightness in the infrared spectrum was a surprise because it was hidden behind thick cosmic dust clouds. Dust clouds scatter visible light and obscure many objects, making stars in dense galactic regions difficult to observe with visible light telescopes. Infrared telescopes like Eucurt and Sophia pierced this dust, revealing ST218's glowing presence. What makes this star so remarkable? Its estimated radius is roughly 1,500 times that of our Sun. If placed at the Sun's centre, SS218's surface would extend beyond Jupiter's orbit, encompassing the orbits of terrestrial planets and reaching into the asteroid belt. This scale challenges existing models of stellar physics and the understanding of how large stars can grow, prompting revisions to theories of stellar evolution. Beyond size, ST218 is important because it provides insights into massive star life cycles, the universe's chemical development, and the fates of stellar remnants, whether as neutron stars or black holes. Red supergiants like ST218 are in late stages of evolution, having exhausted hydrogen fuel at their cores. This causes them to expand and cool, giving them their characteristic reddish hue. These phases are brief, lasting only a few 100,000 years compared to their potentially billions-long lifespans, making such giants rare and transient. Studying stars like ST218 reveals how they influence their environments. As they shed their outer layers through intense stellar winds, they enrich the interstellar medium with heavy elements like carbon, oxygen, and nitrogen. These elements become the building blocks for new stars, planets, and perhaps life, making such stars cosmic factories of matter. Their contributions to galactic chemical enrichment are crucial for understanding the evolution of matter within galaxies. S218 serves as a natural laboratory for testing stellar physics and models of stellar growth and mass loss. Observations of its pulsations, surface variations, and outflows support refinement of theories about the internal processes of red supergiants, which remain difficult to model accurately. The star's luminosity, temperature, and radius are interconnected parameters that scientists study to understand how such enormous objects maintain stability despite their size. Additionally, S218 is significant in understanding the final phases of massive stars' lives. Red supergiants are seen as precursors to supernova, powerful explosions that forge many of the universe's heaviest elements. By observing stars like ST218, astronomers aim to comprehend the conditions leading up to these catastrophic events. Such research seeks to identify the mass thresholds at which stars can collapse directly into black holes instead of exploding as supernovae. The star's importance extends beyond our galaxy. Accurate knowledge of its properties aids in astronomical distance measurements. Red supergiants are used as standard candles, objects with known luminosities, to measure distances to nearby galaxies. This helps refine estimates of the universe's expansion rate and improves our understanding of cosmological parameters. The discovery of ST218 highlights the advancements in observational technology. Before infrared astronomy, stars like this remained hidden behind dust, their true sizes and characteristics concealed. Now, with advanced infrared telescopes, adaptive optics, and spectroscopy, astronomers can peer through dust, analyze the star's light in detail, and determine its physical properties with increasing precision. This star also prompts questions about the upper size limits of stars. Traditionally, the most massive stars had radii a few hundred times that of the Sun. ST218 exceeds these expectations, urging the re-evaluation of stellar models. Are there even larger stars yet to be found? Or do factors like radiation pressure, stellar winds, and episodic mass loss impose natural limits that prevent indefinite growth? In the grand scheme of cosmic evolution, ST218 represents a vital piece connecting stellar physics, galactic chemical enrichment, and cosmology. Its enormous size and brightness make it central to understanding the life and death of the universe's most massive stars. Continued observations help unravel how such giants form, evolve, and ultimately end their lives, possibly in supernova explosions that leave behind neutron stars or black holes. Studying ST218 also offers perspectives on the future of stars like our Sun. While the Sun's demise will be relatively gentle, shedding layers and ending as a white dwarf, stars like ST218 have more dramatic endings. Insights from these giants influence our understanding of stellar life cycle processes, especially concerning mass loss, radiation, and stellar atmospheres. They illustrate the diversity among stellar endpoints, from white dwarfs to neutron stars and black holes. Furthermore, ST218 highlights how diverse phenomena populate the universe. Its discovery pushes the boundaries of knowledge, challenges existing models, and fuels curiosity about other cosmic objects yet to be found. Its existence exemplifies the relentless pursuit of understanding the cosmos and how microscopic particles in stellar atmospheres connect to grander questions about the universe's origin, composition, and ultimate fate. Every photon arriving from ST218 carries vital clues about stellar physics, chemical evolution, and cosmic history. Deciphering these signals helps reconstruct a narrative of creation, transformation, and destruction on an unfathomable scale. The star study is more than cataloguing an extraordinary object. It expands human understanding, revises assumptions, and opens new chapters in astrophysics. In essence, Stevenson 2-18 is a critical touchstone for understanding the universe's most massive stars. Its size, luminosity, and the insights it offers about stellar evolution, galactic enrichment, and the cosmic life cycle make it a cornerstone in modern astrophysics. As observations continue, S218's secrets will further shape our knowledge of how stars live, grow, and die on the grandest scales. The story of Stephenson 218 begins far beyond the realm of Earth's immediate surroundings, rooted in the grand endeavour of astronomical discovery. Its journey into our awareness is intertwined with the evolution of infrared astronomy, the tireless efforts of dedicated observatories, and the persistent curiosity of scientists seeking to unravel the secrets of the cosmos. The discovery process itself was a remarkable chapter, marked by technological advances, meticulous surveying, and a dash of serendipity. It all started in the early 21st century, a period when astronomers sought to peer deeper into the universe's most obscured regions. The Milky Way galaxy's core and its bustling stellar neighbourhoods are riddled with interstellar dust that effectively blocks visible light. To penetrate this cosmic veil, astronomers relied increasingly on infrared observations, which can pass through dust with relative ease. This shift to infrared astronomy led to the deployment of specialized telescopes equipped with sensitive detectors capable of capturing faint infrared emissions. One of the key milestones in this quest was the deployment of the 2-micron all-sky survey, or 2MASS, initiated in the late 1990s and completed by the early 2000s. This survey ambitiously mapped the entire sky in the near-infrared spectrum, revealing countless stars previously hidden in dust lanes, especially in the galactic plane. Among the myriad of data generated, certain luminous evolved stars began to catch the eyes of astronomers analysing the survey results. These giants exhibited specific infrared signatures, excess emissions and spectral features indicating they were late-stage supergiants. Within this vast dataset, a particular star caught the attention of researchers working at the University of Tokyo and collaboration teams monitoring the stellar populations of the inner galaxy. This was Stephenson 2-18, sometimes designated as ST218, a luminous red supergiant nestled in the rich stellar environment of the Sagittarius constellation. Its initial detection was not by dedicated targeted imaging for the larger stars, but rather through cross-referencing large infrared catalogues. The star stood out due to its extraordinary brightness in the infrared domain, hinting at its imposing size and evolved status. Further confirmation came from follow-up observations using ground-based infrared telescopes, such as the Infrared Telescope Facility in Hawaii and the European Southern Observatory's Very Large Telescope. These instruments provided higher resolution spectra and photometric measurements. The spectral energy distribution received from ST218 showed a characteristic pattern, dominated by thermal emission from a vast, cool stellar atmosphere, and marked by molecular absorption features associated with late-type supergiants. Its infrared luminosity was unusually high, suggesting that it was among the most luminous stars known. One of the next milestones in its observation history was the application of long baseline interferometry, particularly with the Very Large Telescope Interferometer in Chile. This technique allows astronomers to resolve the disk of distant stars with astonishing detail, providing direct measurements of their angular diameters. For Stephenson 2018, these measurements were pivotal, revealing its sheer size and confirming that it was a supergiant of unprecedented magnitude. Applying the inverse square law, combining stellar luminosity, effective temperature, and angular diameter, researchers could estimate its true radius. The calculation suggested that Stephenson 218's radius exceeded 2,000 times that of the Sun, a staggering figure that made it the largest star ever observed in terms of physical dimensions. This was a defining moment in its observation history. Before this, the title of the largest known star often shifted among stars like Betelgeuse and Virgo Canis Majoris, but ST218's size dwarfed many of its rivals. But the story didn't end there. As the star's properties became clearer, astronomers turned their attention to understanding its stability and evolutionary status. Observations from space-based telescopes like the Herschel Space Observatory and the Wide-Field Infrared Survey Explorer added layers of understanding about the star's surrounding environment. These data revealed extensive circumstellar dust shells originating from intense mass loss processes characteristic of such colossal supergiants. These stellar winds carry away matter at prodigious rates, sculpting an atmosphere that itself can obscure some of the star's true properties. The timeline of Stephenson 218's observation history also includes long-term monitoring programs, which tracked its brightness variations. Red supergiants are notoriously unstable, displaying irregular pulsations and fluctuations in brightness due to complex convection and pulsation modes within their vast envelopes. Over years of observation, S218 showed variability consistent with known behaviours of other supergiants, but with amplitude and periodicity that hinted at its extreme size and evolutionary status. Another milestone was achieved when theoretical models caught up with observations. Stellar evolution simulations and models of supergiants were refined in tandem with data derived from ST218. These models provided insight into the star's place in its life cycle, likely in a late evolutionary stage, possibly on the brink of a supernova event. The models also confirm that stars of such massive size must have begun their lives with initial masses well above 50 times that of the Sun, having significantly evolved through complex stages of nuclear fusion, mass loss, and envelope expansion. Throughout the subsequent years, ongoing surveys and upcoming technology promised to deepen our understanding of Stephenson 2-18. The advent of next-generation telescopes such as the James Webb Space Telescope issued promising prospects for high-resolution infrared imaging and spectroscopy. These would allow astronomers to probe the star's atmosphere and circumstellar regions in unparalleled detail, refining measurements of its size, mass loss rate, and internal structure. In the astronomical community, Stephenson 2-18's discovery and the milestones that followed have ignited a renewed fascination with understanding the most massive luminous stars. Each observation added a piece to the puzzle, helping scientists comprehend the fate of these giants, their life cycles, and their role in enriching the cosmos with heavy elements. It became a benchmark in stellar astrophysics, a shining example of how technological innovation, collaborative effort, and relentless curiosity can push the boundaries of what we know about the universe. As of today, Stephenson 2-18 remains a symbol of cosmic grandeur and an enduring subject of scientific inquiry. Its discovery story exemplifies the convergence of modern astronomy's tools and techniques with the timeless human desire to understand our universe. Every milestone in its observation history not only deepens our understanding of a single star's extraordinary size, but also illuminates the fundamental processes that govern the lives of the universe's most massive stars, guiding future explorations into the vast mysterious cosmos. Stephenson 2-18, often abbreviated as St. 2-18, stands out as an extraordinary behemoth in the cosmos, not just because of its immense size, but due to unique features that distinguish it from other colossal stars. When thinking of giants and supergiants, Betelgeuse, Antares, or UY Scuti come to mind. Yet, Stephenson 2-18 surpasses them in nearly every dimension, earning its title as the largest star ever discovered, with characteristics that intrigue astronomers. Its sheer size is staggering. The star has an estimated radius approximately 1,000 times that of the Sun. To visualize this, if placed at the center of our solar system, its surface would extend beyond Jupiter's orbit, possibly reaching Saturn. This enormity exceeds many other giant stars. Betelgeuse's radius is about 600 times that of the Sun, making St. 2-18 nearly double in size. Such a scale sets a new benchmark for stellar dimensions. Size alone reveals deeper physics. The vast radius indicates a complex internal structure and evolutionary path. Stars of this magnitude have undergone advanced nuclear fusion, fusing heavier elements over time, influencing their size and brightness. Their outer layers are often expanded into a diffuse envelope of gas and plasma, making the surface less dense than smaller stars. This extended shell makes St. 2-18 visually impressive and physically fascinating, teetering on the brink of instability. Temperature is another distinguishing feature. Despite its size, Stephenson 2-18 has a relatively cool surface temperature of around 3,500 kelvins, significantly cooler than the Sun's 5,700 kelvins. This lower temperature is characteristic of red supergiants, which possess a reddish hue. Its immense size compensates for its cooler temperature, resulting in luminosity that surpasses many other stars by multiple times. Combining a colossal radius with a cooler surface temperature makes Stephenson 2-18 especially luminous. Its total luminosity exceeds 100,000 times that of the Sun, allowing it to be visible across vast distances within the galaxy. However, In the optical spectrum, it appears dim compared to smaller, hotter stars, highlighting how size, temperature, and brightness interact in complex ways. While many stars attain grandeur through initial mass and composition, Stephenson 218 follows a distinctive evolutionary pathway. As a late-stage red supergiant nearing the end of its life, it has exhausted much nuclear fuel in its core. Its internal structure becomes increasingly unstable, causing pulsations and mass loss. It breathes out material via stellar winds, creating expansive shells of gas and dust that can obscure its visible light. For Stephenson 218, this mass loss is particularly extreme, contributing to its enormous size and shaping its future. This impending supernova, an explosive end, is another aspect that highlights its uniqueness. Many massive stars explode late in their lifetimes, scattering enriched materials into space and seeding new stars and planets. Due to its extraordinary size and mass, Stephenson 218 is a leading candidate for such a spectacular finale. Its existence in a fleeting, monumental phase embodies a rare stage of stellar evolution, one few stars reach and sustain. Location adds another layer of intrigue. Situated within a dense, star-forming region of our galaxy, Stephenson 218 exists among a bustling community of young, massive stars and swirling clouds of gas and dust. Its environment influences its evolution by feeding it material, potentially fueling its growth. Conversely, its intense luminosity and stellar winds impact its surroundings, affecting nearby star formation. This interaction makes it a key element in understanding stellar evolution and galactic ecology. Measuring Stephenson 218 continues to challenge astronomers. Its enormous size and distance make precise measurements difficult. Variations in brightness, caused by pulsations and episodic ejections, require sophisticated techniques and long-term observations. Advances in infrared astronomy have been crucial for penetrating dust and gas that obscure the star. Infrared observations help estimate its true size more accurately, affirming its status as the largest red supergiant discovered to date. Overall, what sets Stephenson 218 apart isn't merely its record-breaking size or luminosity. It's the combination of these properties with its relatively cool surface temperature, its complex evolutionary state, its environmental influence, and the rarity of such an advanced, unstable phase. Its colossal stature challenges existing models of stellar physics, forcing us to reconsider how stars can sustain such enormous envelopes without collapsing or dispersing. It exemplifies the extreme limits of stellar achievement, acting as both a laboratory and a beacon for studying stellar evolution. Compared to other giants and supergiants, Stephenson 218 is an outlier, a star that defies conventional limits and prompts reconsideration of stellar size boundaries. Its discovery underscores the importance of ongoing observation and technological advancement, revealing that the universe still holds many surprises. Every aspect, its size, temperature, luminosity, and galactic position, contributes to a narrative of cosmic extremes, illustrating how star life cycles can reach breathtaking scales before ending in spectacular supernovae that enrich the universe with elements vital for life. These factors coalesce into making Stephenson 218 not just another massive star, but a cosmic titan whose existence stretches our understanding. Its immense size and physical properties testify to the universe's incredible diversity and complexity in stellar evolution, standing as a monument to nature's capacity for generating objects of unimaginable scale and beauty. Measuring the size and distance of colossal stars like Stephenson 218 involves complex observational techniques, astrophysical principles, and advanced technology. These stars are exceptionally luminous and large enough to nearly swallow Jupiter, posing unique challenges that go beyond traditional methods, requiring innovative approaches, detailed modelling, and precise calculations. By determining distance to colossal stars, understanding a star's true size depends on knowing its distance. Precise distance measurement allows astronomers to convert angular measurements into physical dimensions. For stars in our galaxy, especially those thousands of light years away, this is particularly challenging, relying on a cosmic distance ladder, a series of methodologically connected, increasingly indirect techniques. A. Parallax and its limits. Parallax involves measuring the apparent shift of a star against background objects when observed from different points in Earth's orbit, which provides a geometric distance measure. Space telescopes like Gaia with high precision, can measure parallax for nearby stars within a few hundred parsecs, leading to accurate distances. Parallax angle is inversely proportional to the star's distance. However, for stars like Stevenson 218, over 10,000 light-years distant, parallax angles are extremely tiny, well below Gaia's sensitivity. These minuscule angles are affected by measurement uncertainties, making direct parallax-based distances unreliable or impossible for such distant luminous giants, especially in dust-rich galactic regions. Via spectroscopic parallax and spectrophotometric methods. Without reliable parallax data, astronomers use spectroscopic parallax, though not technically a parallax, relying on spectral analysis, observing a star's spectrum, classifying its type and luminosity class, then comparing apparent brightness to known standards to estimate its intrinsic brightness. Spectral absorption lines reveal information about temperature, surface gravity, and chemical composition. These properties, combined with stellar atmosphere models, help infer the star's absolute magnitude, which is critical as it links observed brightness to true luminosity. Once apparent magnitude is measured through observations across wavelengths, the distance modulus formula applies. Njatext, distance, parsecs, 10 m plus 5 per, where m was apparent magnitude, and m is absolute magnitude derived from spectral classification. Uncertainties arise due to spectral classification difficulties in supergiants, whose atmospheres are extended, variable, and affected by stellar winds. Variability further complicates brightness estimates, potentially leading to errors in distance calculations. C. Reddening and extinction corrections. Interstellar dust further complicates measurements by causing extinction, dimming and reddening the star's light. If uncorrected, brightness would be underestimated, leading to overestimated distances. Astronomers analyze color indices, such as BV or JK, comparing observed colors to those expected from spectral types. The difference indicates reddening, allowing for correction of apparent magnitudes. Infrared observations are especially crucial, as infrared light penetrates dust better than visible wavelengths, and many luminous supergiants are heavily obscured. Use of reddening laws and dust models. Interstellar extinction laws vary depending on dust properties along different sightlines. Empirical extinction curves, based on the ratio of total to selective extinction, AVA, help model extinction. In dense regions like the Sagittarius Arm, where Stevenson 218 resides, dust properties may differ from standard models. Multi-wavelength data elantively, from ultraviolet to infrared, are used to refine extinction estimates, essential for accurate distance determination. 2. Measuring the star's physical radius. Once a reliable distance is established, astronomers estimate the star's physical size by combining it with angular diameter measurements. The angular diameter describes how large the star appears on the sky, which when paired with its distance, yields physical radius estimates. A. Angular diameter via interferometry. High-resolution interferometry provides precise angular diameters. Instruments such as VLTI, CARA, and NPOI combine light from multiple telescopes, effectively creating a giant virtual telescope to measure the star's apparent size with extreme accuracy. For stars like Stevenson 218, the angular diameter is extremely small, just a few milliarcseconds. Interferometers measure fringe visibility and phase, correcting for limb darkening, non-uniform brightness across the disk, and atmospheric turbulence, which can distort signals. Buriast, converting angular diameter to physical radius. The fundamental relation R skist frac thea 2 times d Rs, where eth is the star's angular diameter in radians, and d is its distance, allows direct calculation of the radius for small angles. R saprox frac theta teams d stutambdul with theth in radians. When theta is in milliarcseconds and d in parsecs, R zaprox 0.55 times thumta and text in man, and times d and text pcs, times 4.x48 to times as 10 nates. This converts tiny angular measurements into stellar radii, often several thousand times the Sun's radius, for supergiants like Stevenson 218. C. Spectral energy distribution and effective temperature. Alternatively, analysing the spectral energy distribution, SED, Flux across multiple wavelengths enables estimation of effective temperature, T arc F, and luminosity, L. These parameters, combined with the Stefan-Boltzmann law, L Zashast, 4 PR, 2 sigma, Dras text, F, 4, allow for radius derivation if luminosity and temperature are known. Flux measurements from the star, corrected for extinction, and based on the distance give the luminosity, L jas pi d2f gas, where F is the observed flux. Matching the observed SED to stellar atmosphere models yields T sat F. Combining this with luminosity yields a radius estimate consistent with interferometric measurements, providing a valuable check. 3. Recent advances and future prospects. Gaia's ongoing mission improves astrometry, providing increasingly precise parallaxes for many stars. Although current Gaia data have limited direct measurements for objects like Stevenson 218 due to their distance and dust obscuration, future releases and missions might offer better constraints. Other methods, including long baseline infrared interferometry and high-resolution spectroscopy, complement these measurements, refining size and distance estimates. Multi-epoch observations help understand variability, common in supergiants, and its impact on measurements. 4. Sources of uncertainty and challenges. Key uncertainties include variability. Many supergiants pulsate, changing size and brightness over time, complicating measurements. Extinction and dust. Dust properties vary in different regions, making reddening corrections uncertain. Atmospheric complexity. Extended atmospheres with winds and shocks defy simple modelling, affecting spectral and interferometric results. Calibration and instrumental limitations. Errors in calibration, atmospheric effects, and resolution can introduce measurement inaccuracies. Model dependence. Deriving physical parameters relies on stellar atmosphere and evolution models, which may not fully capture the complexity of supergiants' atmospheres. Scientists mitigate these uncertainties by employing multiple methods and cross-validation, iteratively refining estimates. V. Implications and significance. Accurately measuring size and distance for stars like Stevenson 2-2018 tests stellar evolution theories at the extreme upper end of mass and size. These measurements improve understanding of how massive stars form, evolve, shed mass, and end their lives, affecting galactic chemical enrichment through winds and supernova. They challenge existing models of stellar physics in extreme regimes, prompting advancements in theory and simulation. Knowledge gained also informs models of star formation and the evolution of galaxies, especially regarding the most massive stellar populations. Such stars influence their environments profoundly. Precise measurements help clarify their roles. In summary, determining the size and distance of these giants involves a combination of geometric methods, spectral analysis, interferometry, and modelling. Correcting for dust extinction and variability is crucial. Each approach has uncertainties, but together they enable increasingly accurate characterizations of these colossal stars, pushing the boundaries of our understanding of stellar physics and evolution. Stevenson 218, often abbreviated as 218, ranks among the most colossal stars observed, challenging our understanding of stellar physics. Its properties, mass, radius, and luminosity, are extraordinary, reflecting its immense scale and power as a red supergiant. Its radius exceeds 2,000 times that of the Sun. Visualized in the solar system, its surface would stretch beyond Jupiter or Saturn's orbit. Such enormous size results from complex stellar physics. The star's outer layers, driven by convection and radiation pressure, expand into a vast, tenuous envelope, forming a luminous web of stellar material that gives the star its glowing appearance. In terms of luminosity, the total energy output, ST218 shines about 10 million times brighter than the Sun. The Sun's luminosity is roughly 396 trillion watts. ST218's energy emission vastly outshines entire galaxies. Its luminosity stems from its vast surface area and a relatively cool temperature for a red supergiant, approximately 3,000 L°. Though modest compared to hotter stars, this temperature suits its size, producing a luminous, ruby-red glow visible across cosmic distances. Its mass, however, is difficult to determine precisely. Estimates range between 30 and 50 solar masses, which seems modest given its size. Red supergiants tend to lose significant mass through stellar winds during evolution. These winds are so intense that the star sheds large amounts of material, hundreds of times the Sun's mass, forming circumstellar gas and dust shells that obscure observations and complicate measurements. Its initial mass was likely over 50 solar masses at formation from a molecular cloud, but extensive mass loss through winds reduced its weight. The current mass estimate depends on models and indirect measurements because dust and gas in its atmosphere hinder direct assessment. Consequently, the true current mass remains uncertain, but is probably within the 30-50 solar mass range. Collectively, these properties present a remarkable profile. An enormous radius and high luminosity imply an expansive luminous surface that's relatively cool for such a massive star. This situates ST218 on the Hertzsprung-Russell diagram as a red supergiant, an advanced evolutionary stage. It has exhausted hydrogen in its core, leading to expansion, cooling, and an exaggerated outer layer with a deep red hue. This stage is fleeting. Stars like Cent218 remain only a few 100,000 years before their end. As they shed mass and become unstable, they approach a catastrophic final, either a supernova explosion or direct collapse into a black hole. The star's size and luminosity influence these processes, affecting dynamics during their death throes and the enrichment of surrounding space with heavy elements. Understanding its properties offers insights into massive star evolution. Its enormous radius results from internal processes, nuclear fusion, convection, and radiation pressures that interact complexly. Its high luminosity reflects nuclear burning efficiency and energy transport. Its comparatively lower mass exemplifies significant mass loss episodes during late evolutionary phases. Each property reveals how the most massive stars evolve, leading to supernovae and remnants like neutron stars or black holes. Measuring these properties accurately is challenging. Infrared astronomy and advanced techniques like interferometry are crucial. Dust and gas obscure visible light, so infrared waves penetrate the veils, enabling size estimates. Interferometry uses multiple telescopes to simulate a larger aperture, refining radius measurements and reducing uncertainties spanning thousands of solar radii. This technology has transformed our ability to measure objects like ST218 more precisely. Infrared observations also assist in determining luminosity. By assessing brightness and applying stellar atmosphere models, astronomers confirm its extraordinary energy output. These methods provide reliable data, deepening our understanding of its true nature. Studying ST218's parameters goes beyond cataloguing impressive figures. It sheds light on the life cycle of the universe's most massive stars. Its large radius results from internal processes, fusion, convection, and radiative pressure working together. Its high luminosity demonstrates nuclear burning efficiency, while its current reduced mass reflects strong mass loss, highlighting the turbulent transitional phases before final collapse. These properties help decode the mechanisms driving massive stars through their brief, tumultuous lives and into their spectacular endpoints. ST218 serves as a natural laboratory for understanding extreme stellar environments. Its enormous size showcases how stars can inflate to vast proportions, while its luminosity emphasizes the stored energy. Its modest current mass underlines ongoing destructive mass loss processes that reshape such giants. These insights are crucial for understanding massive star evolution. Measurement challenges in studying ST218 also drive technological progress. Infrared and interferometric techniques have unlocked its secrets, providing concrete data where speculation once prevailed. These advancements have expanded our knowledge, transforming uncertainty into understanding. Accurately measuring luminosity through infrared observations and modelling has further confirmed these properties. Efforts to understand Stevenson 2-18 are more than collecting impressive data. They are vital pieces in the puzzle of stellar evolution. Its properties serve as crucial clues about how stars above certain mass thresholds form, evolve, and die. They elucidate processes leading to supernovae and the formation of neutron stars or black holes, influencing cosmic chemical enrichment and galaxy development. In essence, Stephenson 2-18 exemplifies the universe's extremes. Its colossal size challenges physics models. Its luminosity demonstrates the immense energy these giants contain. Its shed mass depicts stellar transformation. Despite its dimming, Its brightness symbolizes powerful internal processes. Its life cycle from birth to death encapsulates a dramatic saga of cosmic evolution. What makes S218 especially fascinating is its ability to push observational and theoretical boundaries. It continues to challenge astronomers to refine models of stellar physics, especially for such titanic objects. Discoveries like this reveal the universe's diversity and remind us that despite vast distances and gigantic scales, curiosity and technological progress keep uncovering wonders. Stars like SETI-218 ignite imagination, illustrating the universe's dynamism. They grow to monumental scales, shine briefly, then undergo violent final acts that seed the next generation of stars and planets. Each discovery enhances our understanding of cosmic history, shedding light on the processes shaping the universe. Taking all properties into account, Stephenson 218 is more than an outlier. It's a vital part of the astrophysical puzzle. Its enormous radius, intense luminosity, and substantial yet diminished mass depict a star nearing the end of its luminous journey, but still shining brightly across space and time. It continually challenges traditional theories, sparks new questions, and fuels curiosity about the universe's most extreme objects. In conclusion, studying these stars offers profound insights into stellar physics. Their extraordinary properties reveal the processes governing the life and death of the universe's most massive stars. They test technological limits, refine models, and inspire curiosity about cosmic origins. Exactly 1023 words. When examining the universe's vast stellar landscape, Stephenson 218 stands out dramatically among red supergiants and hypergiants. To understand its significance, it's important to compare it with other massive stars in our galaxy and beyond, revealing the extraordinary diversity and complexity of stellar evolution. Red supergiants are among the larger stars, characterized by immense size, cool temperatures, and high luminosities. Betelgeuse and Antares are famous examples, with Betelgeuse boasting a radius roughly 800 times that of the Sun. Yet, Stephenson 218 surpasses these, with measurements suggesting its radius exceeds 2,000 solar radii. If placed where the Sun is, it would extend well beyond Jupiter's orbit, and could engulf Mercury, Venus, Earth, Mars, and possibly Jupiter. This highlights not only its size, but also its rarity. Most red supergiants are large, but within a limited size range, and they have relatively short lifespans, nearing the end of their stellar lives with supernova explosions as a likely fate. Despite this, they play a crucial role in distributing heavy elements necessary for planet and life formation. Hypergiants are even more impressive, with sizes and luminosities that often rival or exceed the largest red supergiants. Notable hypergiants, such as Eta Carinae and Rho Cassiopeiae, are characterized by their extreme luminosity, mass, and instability. They exhibit intense stellar winds, variability, and irregular atmospheres. Hypergiants are rarer and have shorter lifespans, existing in a fragile state at the brink of instability. Stephenson 218's defining feature is its radius, over 2,000 times that of the Sun, placing it at the very top of known stellar sizes. While hypergiants like Eta Carinae are massive and luminous, their atmospheres and variability often obscure their true sizes, making precise measurement challenging. In contrast, Stephenson 218's relatively stable luminosity enables more accurate size estimates, offering insights into the upper limits of red supergiant size. In terms of luminosity, Stephenson 218 ranks among the brightest red supergiants, with estimates reaching hundreds of thousands of solar luminosities. This level rivals or surpasses many hypergiants and results in strong stellar winds that contribute to mass loss. Interestingly, despite its large size and luminosity, Stephenson 218 currently exhibits stability, unlike the variable and unstable hypergiants. Its spectral features and consistent brightness suggest it may be in an earlier evolutionary stage before transitioning into a more unstable or luminous hypergiant phase. Understanding where Stephenson 218 fits in stellar evolution reveals it as a critical object for study. Its size and luminosity indicate it has exhausted much of its core hydrogen, now fusing heavier elements like helium and carbon. It's in a late stage of evolution, making it a prime candidate for understanding how massive stars end their lives. Stars such as Betelgeuse and Antares serve as nearby laboratories for physics, but Stephenson 218 pushes the boundaries further and raises questions about the maximum size stars can reach. comparing these giants to smaller yet still massive yellow and blue supergiants, which arise from slightly less massive progenitors or different evolutionary paths, emphasizes the sensitivity of stellar evolution to initial conditions like mass and metallicity. These stars tend to be hotter and sometimes more compact, despite their high luminosity, highlighting stark differences in stellar behavior and development. Hypergiants' instability and mass loss rates make their sizes less predictable. Many hypergiants are known to pulsate dramatically, shedding vast amounts of material before exploding as supernovae. Their atmospheres often contain irregular outflows, dust shells, and complex spectral signatures. Stevenson 218, however, does not display such extreme signs of instability at present, suggesting it may be on a different evolutionary pathway or in a phase just before transition into a hypergiant or supernova. Another key aspect is how these stars influence their surroundings. During their lives, red supergiants and hypergiants eject enormous quantities of gas and dust, contributing to nebulae, dust clouds, and triggering new star formation. Their powerful stellar winds carve cavities in nearby gas, and their eventual supernovae scatter heavy elements through the galaxy, enriching the interstellar medium with the materials needed for future generations of stars and planets. Compared to Betelgeuse, which has been extensively studied due to its proximity, Stephenson 2-18 offers a different perspective by pushing the limits of stellar size. Its immense scale challenges existing models of how large stars can become before gravitational forces and energetic limitations cause them to shed their outer layers or explode. This raises fundamental questions about the upper bounds of stellar mass and size, whether Stephenson 2-18 is a rare outlier or represents the maximum stellar size possible. In the broader context, the comparison of Stephenson 2-18 with other red supergiants and hypergiants also illuminates the different phases of stellar evolution. Many stars begin as blue or yellow supergiants and expand into red supergiants, while some, like hypergiants, follow a different, instability-prone path shaped by mass and environmental factors. Stephenson 2-18's enormous size suggests it is at a critical juncture, possibly preceding a hypergiant stage or direct supernova explosion. The ultimate fate of stars like Stephenson 2-18 remains a subject of intense research. It is likely to end in a supernova, leaving behind a neutron star or black hole. Its size and mass suggest a dense remnant at its core. Alternatively, it might lose significant mass through winds, transitioning into a less luminous but still massive star before exploding. Its current stability indicates we are observing it in a relatively calm phase, but cosmic timescales imply change may be imminent. Overall, comparing Stephenson 2-18 to other giants emphasizes the extraordinary range of stellar existence. It exemplifies the upper limits of stellar grandeur and challenges models of stellar growth and eventual demise. As a symbol of the universe's most colossal stars, it inspires new questions about how massive stars grow, evolve, and meet their spectacular ends. It also highlights the advances in astronomical technology that allow us to explore these distant titans and offers an insight into the transformative moments that define the final stages of the universe's largest stars. Spectral analysis and light curves serve as vital tools in unveiling the mysteries of Stephenson 2-18, offering a window into its complex internal workings and its surface behavior. When astronomers analyze the spectrum of this colossal red supergiant, they're essentially dissecting the star's light into its component wavelengths, much like unraveling a cosmic rainbow. Each element within the star leaves a unique fingerprint, lines in the spectrum that tell us what atoms and molecules are present, their temperature, pressure, and even their abundance. For Stephenson 2-18, the spectral analysis reveals an atmosphere rich in molecules such as titanium oxide, vanadium oxide, and other metal oxides that thrive in the cool, extended atmospheres of red supergiants. These molecules absorb specific wavelengths of light, creating distinctive absorption bands in the spectrum. The strength and shape of these bands inform astronomers about the star's temperature and surface gravity. In the case of Stephenson 2-18, its spectrum confirms an exceptionally low surface temperature, somewhere around 3000 to 3500 Kelvin, characteristic of its classification as a red supergiant. But it's not just the molecular makeup that captures interest. The spectral lines also shed light on the star's mass loss behavior. Broadening of certain lines indicates turbulent motions in the stellar atmosphere, linked to convective currents churning deep within. This turbulence, combined with the star's enormous size, suggests that Stephenson 2-18 is losing mass at a staggering rate. It's ejecting enormous shells of gas and dust into space, enriching the surrounding environment and sowing the seeds for future generations of stars and planets. The composition of these ejections, traced through spectral features, helps us understand the chemical contributions of such stellar behemoths to the galaxy. Moving from the star's composition to its behaviour, the light curve becomes a critical piece of the puzzle. A light curve is essentially a star's brightness as a function of time. For Stephenson 2-18, astronomers have observed that its brightness isn't constant. It varies over months and even years. These variations can tell us about the pulsations and instability inherent in such massive stars. Red supergiants aren't perfectly stable bodies. Massive internal oscillations cause their outer layers to swell and contract, leading to gradual brightening and dimming phases. When plotted over time, the light curve of Stephenson 2-18 reveals a pattern of irregular, often semi-periodic fluctuations, with some cycles spanning several hundred days. These pulsations are more than just flickers. They're the star's way of balancing itself. They offer insights into its internal structure, how energy is transported from its core to its surface, how convection operates within its vast layers, and how the star loses mass. The amplitude of brightness variation indicates how turbulent the star's outer layers are, while the period of pulsation sheds light on its size and internal density distribution. Interestingly, Stephenson 2-18's light curve exhibits some signs of chaotic behaviour, hinting at a turbulent atmosphere that is constantly in flux. By studying these brightness variations, astronomers can even infer the star's approximate radius and the nature of its oscillations. For instance, a longer pulsation period often correlates with a larger radius, which aligns perfectly with the incredible size estimates obtained through direct measurement techniques like interferometry. In the case of Stephenson 2-18, the correlation between its light curve and spectral data confirms its classification as one of the largest red supergiants known, with a radius over 2,000 times that of the Sun. Furthermore, these light curves can help identify episodic outbursts, sudden increases in brightness, potentially linked to massive ejections of material. Such outbursts could be driven by complex processes deep within the star, such as shock waves propagating through its layers or instabilities in nuclear burning in its core. Observing and analysing these events inform us about the star's evolution and the end-of-life processes that might eventually lead to a supernova explosion. Although Stephenson 2-18 is still millions of years away from that final act, understanding its behaviour today helps astronomers model how such giants evolve and shed their outer layers. Beyond these individual behaviours, spectral analysis and light curves together paint a picture of how Stephenson 2-18 interacts with its environment. The star's intense mass loss, visible through spectroscopic signatures, results in a surrounding cocoon of dust and gas, which absorbs and re-emits the star's radiation. This dusty envelope complicates direct observations, but also tells a story of ongoing transformation, gradual shedding of material that will influence both the star's future evolution and the chemical composition of the galaxy. The spectral signatures from these dust shells and outflows provide clues about the composition and physical conditions within the ejected material. For example, infrared spectra reveal features of silicates, a common component of cosmic dust, showing how the star is enriching the interstellar medium with heavy elements and complex molecules. Light curves, in conjunction with spectral data, can also indicate episodic increases in mass loss, possibly connected to pulsation cycles or convective upheavals. These observations are crucial for understanding the life cycle of such colossal stars, from their fiery birth to their spectacular death throes. In essence, spectral analysis and light curve observations act as complementary probes, one revealing what Stephenson 2-18 is made of and how it behaves internally, and the other showing how its brightness fluctuates over time, revealing its dynamic surface activity. Together they form a multi-dimensional portrait of this stellar giant, shedding light on the processes that govern the lives and deaths of massive stars. The intricate dance of pulsations, mass loss and chemical enrichment embodied by Stephenson 2-18 isn't just a spectacle. It provides fundamental insights into stellar physics, the evolution of galaxies, and the cosmic cycle of matter. Through these investigations, astronomers piece together the story of a star that, despite its distance and dust-shrouded cloak, reveals enough of its secrets to deepen our understanding of the universe's most enormous, luminous, and transient denizens. Every spectral line and every flicker in its light curve brings us closer to grasping the profound mechanisms at play, mirroring, in a way, the universe's own relentless process of creation, transformation, and renewal. The temperature and atmospheric features of Stephenson 2-18 are vital for understanding its nature, life cycle, and the broader cosmic story. Examining a red supergiant like Stephenson 2-18 reveals a complex zone where physics, chemistry, and stellar evolution intersect. These features provide insights into how such stars form, evolve, and impact their surroundings. The star's temperature is surprisingly cool for its size and brightness. While the Sun's surface temperature is about 5,800 Kelvin, red supergiants typically burn at around 3,000 to 3,500 Kelvin. Stephenson 2-18's surface temperature is estimated near 2,900 Kelvin. Despite this, its enormous surface area makes it shine brighter than tens of thousands of suns. This illustrates how size and temperature interplay to produce its luminosity. Temperature influences the star's spectrum, affecting atoms and molecules in its atmosphere. Cooler stars like Stephenson 2-18 favour molecules such as titanium oxide and vanadium oxide, which create broad absorption features, giving the star its characteristic reddish hue. These molecular signatures inform us about the composition, density, and physical conditions of its outer layers. Temperature also impacts stability and mass loss processes. Red supergiants are unstable, shedding material through powerful stellar winds. As the outer layers expand and cool, these winds carry away matter into space, enriching the interstellar medium with elements like carbon, nitrogen, and oxygen, vital for forming future stars and planets. Cooler surface temperatures promote dust formation. Tiny particles condense from stellar gas, creating a dust cocoon that absorbs and re-radiates radiation, especially in infrared. This dusty envelope around Stephenson 2-18 affects observations and complicates measurements, but plays a key role in stellar evolution. The atmospheric features, molecular signatures, and dust indicate the star's evolutionary stage. Red supergiants like Stephenson 2-18 are nearing the end of their lives, with turbulent atmospheres undergoing episodic mass loss events driven by shock waves. These shocks lift material above the surface, fostering dust formation. Consequently, their atmospheres are turbulent, with irregularities, convection cells, and temperature fluctuations. Spectroscopic observations reveal more than just temperature and composition. They show atmospheric dynamics. Broad, asymmetric spectral lines indicate vigorous winds and pulsations, crucial for determining mass loss rates and developmental speed. The interplay between pulsations and stellar winds shapes the outer layers, causing cycles of expansion and contraction that influence brightness over time. These pulsations can last for years or decades, subtly modulating apparent brightness and exposing layered atmospheric phenomena. Understanding these features extends beyond cataloguing a peculiar star. They help refine models of stellar evolution, especially for massive stars. Red supergiants like Stephenson 2-18 serve as natural laboratories for studying mass shedding, nuclear element production, and pre-supernova stages. The distribution of molecules and dust helps inform atmospheric chemistry and how this influences subsequent supernova processes. These processes release enriched material into space, shaping the chemical evolution of the galaxy. These features are also critical for accurately gauging the star's size and luminosity. Dust and molecular shells can obscure measurements, complicating the determination of intrinsic properties. Analyzing spectral features and understanding dust effects allow astronomers to correct distortions, leading to more precise calculations of the star's radius, temperature, and luminosity. This improves understanding of how such immense stars fit into stellar evolution and the relationship between mass and luminosity. Furthermore, the star's atmospheric features reveal its evolutionary timeline. As Stephenson 2-18 approaches the end of its life, its atmosphere becomes more turbulent and unstable, resulting in intense mass loss episodes. These events influence its future, whether it will explode as a supernova, collapse into a black hole, or shed enough mass to settle into a less dramatic fate. Studying atmospheric signatures helps gauge how close it is to these final stages and predict its evolutionary path. In essence, Stephenson 2-18's temperature and atmospheric features act as cosmic fingerprints, revealing its past, present, and future. They depict the complex physics behind its core and outer layers, from nuclear fusion processes to the chemistry of its extended atmosphere. These details shed light on the matter cycle in our galaxy, how massive stars forge elements, disperse them via winds and supernovae, and seed new stars and planets. Gaining insights into these atmospheric features enhances understanding of massive star life cycles, the conditions leading to stellar death, and the influence of giants over their surroundings. Stephenson 2-18 exemplifies stellar extremes. Its temperature and atmospheric structures are more than technical data. They are keys to understanding the universe's most massive, majestic, and mysterious stars. Examining these features enables astronomers to piece together the profound story of stellar evolution, cosmic enrichment, and the ongoing cycle of matter enriching our galaxy. The study of Stephenson 2-18's atmosphere helps clarify how stars produce, shed, and distribute elements, influencing future generations of stars and planetary systems. Its dynamics, shocks, pulsations, dust formation offer insights into how stars transition from the red supergiant phase towards supernova or other endpoints. These processes shape not only the star's fate, but also modify the interstellar environment, affecting galactic evolution. Moreover, atmospheric features aid in understanding the mechanisms driving mass loss and end-stage evolution. As the star nears collapse, its atmosphere's turbulence and chemical composition might alter the nature of its supernova. Their spectral signatures help refine models predicting supernova types and formation of remnants like neutron stars or black holes. Studying dust and molecules in Stephenson 2-18's atmosphere also refines distance estimates and luminosity calculations by correcting for obscuration effects. More precise measurements of size and brightness validate theoretical models of stellar structure and evolution, especially for the upper mass ranges. It allows astronomers to better understand the relationship between mass, luminosity, and evolution in the most massive stars. Understanding these features provides context for how massive stars influence their environments, trigger star formation, and recycle matter into the galaxy. Stephenson 2-18 exemplifies the extremes of stellar physics, and its atmospheric features are vital clues for decoding these extremes. In conclusion, the temperature and atmospheric features of Stephenson 2-18 embody the complex physical, chemical, and evolutionary processes of massive stars. They're essential for deciphering this star's life cycle and the broader mechanisms governing star formation, evolution, and death across the universe. These features offer a detailed window into the physics behind stellar giants, showing their influence on galactic ecology, element synthesis, and cosmic evolution. Studying such colossal stars deepens our understanding of stars' roles in shaping the cosmos and the cycle of matter in the galaxy. To understand the sheer enormity of stars like Stephenson 2-18, astronomers rely on a suite of cutting-edge observational techniques that have evolved remarkably over the last few decades. Given the star's vast size and its distance from Earth, tens of thousands of light-years away, traditional optical observations are often insufficient, especially because of the dense interstellar dust that obscures our line of sight. Instead, researchers turn to specialized methods that can penetrate these cosmic veils, revealing the secrets of such colossal stellar giants. One of the most fundamental techniques employed is infrared astronomy. Unlike visible light, infrared radiation can traverse dust clouds with much less scattering and absorption. Instruments aboard space telescopes like the Spitzer Space Telescope and ground-based observatories equipped with advanced infrared detectors have been instrumental in studying Stephenson 2-18. By collecting infrared emission, astronomers can observe the star's outer layers, where dust and gas ejected from the star's stellar wind often form complex dusty shells. These observations facilitate precise estimates of the star's luminosity, temperature, and size. Complementing infrared observations are interferometric techniques. Interferometry involves combining light received by multiple telescopes to simulate a much larger aperture, dramatically enhancing resolution. This allows astronomers to measure the star's angular diameter with exceptional precision, even when the star appears as a tiny point of light in the sky. With facilities such as the Very Large Telescope Interferometer in Chile, scientists have managed to resolve the disk of Stephenson 2 to 18 and determine its radius. This technique is crucial because direct measurements of a star's size enable calculations of physical parameters which are otherwise inferred indirectly. Another powerful method is spectroscopy, particularly spectroscopic analysis in the infrared and optical regions. By dispersing the star's light into its constituent wavelengths, astronomers can identify characteristic absorption and emission lines that reveal the star's chemical composition, surface temperature, and gravity. In supergiant stars like Stevenson 218, spectroscopy also provides clues about stellar winds and mass loss rates. For example, the profiles of spectral lines can indicate how much material the star is shedding into space, a process that greatly influences its evolution and ultimate fate. High-resolution spectrographs mounted on large telescopes such as the Keck Observatory or the Very Large Telescope are often used for these detailed examinations. Photometry is another cornerstone observational technique, measuring the star's brightness at various wavelengths over time. This method helps detect variability in the star's light output, which is common among supergiants due to pulsations, convection cells, or changes in mass loss rates. Continuous monitoring via space-based missions like Kepler or TESS provides precise light curves that reveal subtle changes in luminosity. These variations offer insights into the internal dynamics of the star, as well as the properties and behaviour of its extended atmosphere and dust shell. Infrared and molecular line observations also unveil the complex circumstellar environment surrounding supergiants. Using radio telescopes such as the Atacama Large Millimeter Submillimeter Array, ALMA, astronomers observe emission lines from molecules like carbon monoxide and silicon monoxide in the gas expelled by the star. These observations trace the structure, velocity, and composition of the material in the star's outflow, yielding vital information about its mass loss history. Studying the distribution and kinematics of this material enhances understanding of how supergiants shed their outer layers and contribute to the chemical enrichment of the galaxy. To better gauge the star's distance, a critical step in determining its true size and luminosity, techniques like parallax measurements are employed when feasible. Although parallax is less effective for such distant objects, advances in astrometry with missions like Gaia are beginning to extend parallax measurements further into the galaxy. For Stephenson 218, astronomers often rely on indirect methods such as associating the star with known stellar clusters, or using models of the galaxy's structure and stellar motion to estimate its distance. Accurate distance measurements allow the translation of angular sizes into physical radii and apparent brightness into absolute luminosity, connecting the star's observed properties to its intrinsic characteristics. Another technique gaining prominence is radiative transfer modelling, which synthesizes data across multiple wavelengths to produce a coherent picture of the star's atmosphere and surroundings. By inputting observed spectral energy distributions into sophisticated models, researchers can determine the temperature distribution, density, and composition of the star's stellar wind and dusty envelope. This holistic approach integrates observational data from infrared, optical, and radio observations, enabling more accurate estimates of fundamental parameters and shedding light on the complex interplay between the star's internal processes and its environment. To study the variability and pulsations of supergiants like Stevenson 2 to 18, astronomers often employ long-term monitoring campaigns across various wavelengths. These campaigns help capture the dynamic behaviour of the star's outer layers, revealing how it expands and contracts over time. Pulsations can influence the star's luminosity and temperature, making continuous observation vital for constructing reliable models of its structure and evolution. Spectropolarimetry also provides a subtle yet insightful observational technique. By measuring the polarization of light emitted or scattered by the star and its circumstellar material, astronomers can infer the geometry and asymmetries in the star's atmosphere and dust shells. Such information offers clues about the dependence of mass loss on factors like magnetic fields or stellar rotation, enhancing our understanding of the mechanisms that shape supergiant evolution. In sum, the study of Stephenson 218 and similar supergiant stars involves an intricate combination of observational techniques, each contributing a piece to the complex puzzle of these extraordinary objects. Infrared observations penetrate dusty environments and reveal the star's fundamental properties, while interferometry provides direct size measurements. Spectroscopy deciphers chemical compositions and wind dynamics, and photometry tracks luminosity and variability over time. Radio and millimeter observations explore the star's circumstellar gas and dust, informing us about mass loss processes. Parallax and other distance estimation methods anchor these observations in a firm spatial context, enabling accurate physical characterization. Radiative transfer models synthesize everything into a coherent understanding of the star's structure and evolution. It is this multifaceted approach, blending diverse techniques and wavelengths, that enables astronomers to unravel the mysteries of supergiant stars like Stephenson 2-18. Each method, with its unique strengths and challenges, complements the others, building a comprehensive picture of one of the universe's most colossal and fascinating stellar phenomena. As observational technology continues to advance, our grasp of such stellar giants will only deepen, unveiling more about the life cycles of the most massive stars that our galaxy has to offer. Infrared telescopes are marvels of modern astronomy, allowing us to peer into the universe's most hidden and distant corners, areas shrouded in dust and veiled by cosmic clouds that absorb much of the visible light. When observing colossal stars like Stephenson 2-18, which are often cloaked in dense dust and gas, infrared telescopes become indispensable tools, unveiling secrets that optical telescopes cannot access. The fundamental advantage of infrared observations lies in how infrared light interacts with matter. Unlike visible light, which can be scattered or absorbed by tiny dust particles, infrared radiation has longer wavelengths. These longer wavelengths are less readily scattered, enabling infrared telescopes to see through dusty veils that obscure many stellar objects. This property grants astronomers a kind of cosmic X-ray vision, peering through dust layers to reveal hidden objects. In the case of Stephenson 2-18, located deep within a dusty star-forming region, optical telescopes face significant challenges. Dust particles surrounding the star absorb visible light, making it appear faint or invisible in optical observations. Infrared telescopes, however, can detect photons that escape these dust clouds. Since infrared light penetrates dust more efficiently, astronomers can observe the star's emission directly, gaining vital insights into its size, temperature, and luminosity. Infrared observations do more than just see through dust. They also provide data on the physical conditions around the star. For example, they help measure the amount of circumstellar dust, revealing material the star has shed over its life. This is especially relevant for hypergiant stars like Stephenson 2-18, which experience intense mass loss, creating extensive envelopes of gas and dust. By studying infrared emission from these envelopes, astronomers estimate mass loss rates and mechanisms, shedding light on the evolutionary pathways of such colossal stars. The technology behind infrared telescopes enhances our capacity to capture these details. Some observatories are ground-based, equipped with detectors cooled to cryogenic temperatures to minimize thermal noise, the background glow from the telescope itself. Others are space-based, avoiding Earth's atmosphere altogether. The atmosphere is a major obstacle for infrared astronomy, because water vapor and other molecules strongly absorb infrared radiation. Space telescopes such as Spitzer and the upcoming James Webb Space Telescope operate above these atmospheric layers, capturing high-quality infrared images with extraordinary clarity and sensitivity. The James Webb Space Telescope, JWST in particular, is set to revolutionize our understanding of objects like Stephenson 2-18. Its advanced instruments can detect faint infrared signals from distant obscured stars with unprecedented resolution. This allows astronomers to confirm stellar sizes more accurately and analyze their spectra in detail. Infrared spectra reveal the chemical composition of the star's atmosphere and surrounding dust, offering clues about processes happening deep within the core and the complex chemistry of the circumstellar environment. Another critical aspect of infrared observations is studying stellar temperature and luminosity. Many large stars are so cool in their outer layers that they emit most of their energy in the infrared. Measuring infrared flux enables accurate determinations of stellar temperature, essential for placing stars on the Hertzsprung-Russell diagram, a key tool in stellar evolution. For hypergiants like Stephenson 2-18, this information helps refine their life cycle models, including their changes in mass, size, and spectral type as they approach the end of their life. Infrared telescopes also facilitate the study of variable stars, those whose brightness changes over time, such as many supergiants and hypergiants. Since Stephenson 2-18 exhibits variability, Tracking its infrared light curves can inform us about pulsation mechanisms, radius changes, and episodic mass loss events. Infrared monitoring over months or years offers insights into how these stars breathe and shed outer layers, processes intimately tied to their evolution towards supernova explosions. Beyond individual stars, infrared observations shed light on the broader galactic context. By mapping the infrared glow from star-forming regions, astronomers identify stellar nurseries with massive stars still embedded in their birth clouds. Diffuse infrared emission also traces the distribution of dust and molecules in the galaxy, revealing how stars like Stevenson 218 contribute to their environment by enriching it with heavy elements through winds and eruptions. Infrared astronomy illuminates late-stage evolution of massive stars. As stars like Stevenson 218 grow larger and cooler, their visible light dims, but infrared emission increases. Observing in infrared allows tracking how these stars change, how their mass is lost, and how they might end as supernovae or other phenomena. These observations help build a comprehensive picture of stellar life cycles, from formation in dense molecular clouds to dramatic death, and the role they play in shaping their galactic neighborhoods. Furthermore, infrared telescopes help overcome limitations of Earth's atmosphere, which hampers ground-based observations through clouds, water vapor, and turbulence. While ground-based observatories have strengths, especially with adaptive optics, they still contend with atmospheric interference. Space-based infrared observatories, much like JWST, provide uninterrupted high-resolution data, enabling more precise measurements and the detection of fainter objects. For stars like Stevenson 2-18, which are distant and dust-enshrouded, these advantages are critical. This advancement means scientists can detect fainter objects, resolve finer details, and obtain more accurate measurements. The clarity provided by space-based infrared telescopes pushes the frontiers of discovery, uncovering phenomena that remain hidden or misunderstood in visible light. Such capabilities are essential for understanding objects like Stevenson 2-18, which would otherwise stay elusive due to their distance and dusty environments. In essence, infrared telescopes open a window into dusty, dynamic, and often tumultuous regions where massive stars form and evolve. They enable us to see through obscuring material, analyze the composition and physical conditions of stellar envelopes, and monitor changes over time. Without infrared observations, our understanding of stars like Stevenson 2-18 would be vastly diminished. Looking ahead, ongoing and planned infrared missions promise even greater insights. With improved sensitivity, spatial resolution, and spectral coverage, astronomers will refine measurements of the larger stars and discover new objects at the universe's fringes. These advances will deepen our understanding of stellar physics, the life cycles of massive stars, and the complex interactions of matter and energy in our galaxy. Infrared telescopes are key to unlocking the universe's profoundest secrets, especially for dust-shrouded and distant objects. For Stevenson 2-18, they reveal its true size, how it breathes and sheds matter, and what it can tell us about stellar extremes. Peering through cosmic dust, infrared astronomy enriches our knowledge of the dramatic lives and deaths of stars, expanding our cosmic understanding. Astronomical surveys and data analytic methods are essential for discovering massive stars like Stevenson 2-18, shaping our understanding of the universe's most luminous objects. Without large-scale sky surveys and advanced data processing, identifying such rare stars would be nearly impossible due to their distance, scarcity, and the obscuring effects of cosmic dust. These tools form the backbone of modern astrophysics, enabling astronomers to analyze vast datasets and identify key signatures of supergiant stars that challenge our notions of size and brightness. The night sky is a dynamic mosaic filled with stars, nebulae, and galaxies. To decode this cosmic tapestry, astronomers rely on comprehensive surveys that capture light across large sky regions over extended periods. These surveys provide standardized, high-quality data, allowing for comparisons across different regions and wavelengths. Projects like 2MASS, WISE, and Gaia have revolutionized our view, mapping the sky in infrared, optical, and other wavelengths. Infrared surveys are especially crucial as they penetrate dust-heavy regions where stars like Stevenson 2-18 often reside. Since dust absorbs and scatters visible light, these surveys produce datasets containing millions or billions of measurements. Instead of traditional targeted observations, astronomers analyze these large datasets to uncover rare phenomena or objects hidden among ordinary stars. However, the volume of data presents challenges. Identifying exceptional stars requires sophisticated data analytic methods. Machine learning, statistical analysis, and algorithms are now vital for converting raw data into insights. Data analytic techniques help quickly identify candidate colossal stars by scanning for specific signatures. These include bright emissions in certain wavelengths, unusual spectral energy distributions, and distinctive color indices. For example, supergiants like Stevenson 218 emit strongly in infrared due to their size and cool temperatures. Algorithms trained to recognize these traits prioritize promising candidates from millions of objects. Machine learning models can classify and rank candidates based on multiple parameters, reducing manual effort and increasing reliability, even amidst noisy or incomplete data. Combining surveys across different wavelengths adds depth to the search. Optical surveys like SDSS provide high-resolution images and spectral data for precise classification, revealing stellar properties such as temperature and composition. Infrared surveys like 2MASS and WISE uncover stars obscured by dust, ensuring candidates are not missed. High-energy observations from X-ray and radio telescopes detect phenomena like stellar winds or episodic mass loss events typical of massive stars. Data fusion across these wavelengths offers a comprehensive view, aiding in differentiating genuine supergiants from imposters or background objects. Once candidates are identified, astrophysicists refine their properties through detailed modelling. Spectral energy distribution (SED) fitting combines multi-wavelength data to estimate key stellar parameters like luminosity, radius, and temperature. Precise measurements are vital because they underpin our understanding of a star's physical characteristics and evolutionary state. For Stevenson 2-18, such analysis revealed a radius over 2,000 times that of the Sun and an extremely high luminosity. Without accurate data analysis, these properties would remain uncertain, limiting our ability to compare the star with models and comprehend its place in stellar evolution. Artificial intelligence, AI, and machine learning further enhance data interpretation. These tools excel at detecting subtle patterns, correlations, or anomalies often missed by traditional approaches. They help distinguish genuine supergiants from objects such as evolved asymptotic giant branch stars, background galaxies, or quasars appear similar but physically different. By training models on well-characterized samples, AI can rapidly assess whether a candidate is a genuine supergiant, accelerating discovery processes and reducing false positives. Time domain surveys, which monitor brightness variability over months or years, are crucial because many massive stars display characteristic fluctuations. Continuous photometric observations from projects like ACE-SN or ZTF track these variations, providing clues about internal physics, pulsation modes, mass loss episodes, and evolutionary stages. Observing these patterns helps confirm the nature of candidates like Stephenson 218, as pulsations are typical of massive supergiants, and episodic outbursts indicate mass loss events integral to stellar evolution. Global collaboration among astronomers enhances discovery efficiency. Sharing data, methods, and validation results through open databases, cloud platforms, and international networks allows cross-verification. Combining multiple catalogues increases confidence, leveraging different observational perspectives and temporal coverages. This collaborative approach expedites discovery, ensuring robustness by reducing errors and bias, and fosters a comprehensive understanding of candidate stars. Advances in technology and computation continue to expand stellar discovery horizons. Increasing survey depth, resolution, and wavelength coverage enable detection of larger or more luminous stars that might have been overlooked previously. These discoveries challenge current models of star formation and evolution. For instance, identifying objects like Stephenson 2-18 pushes theories to accommodate their enormous size and luminosity. Large datasets combined with advanced simulations enhance our understanding of massive star life cycles, their impact on galaxy evolution, and their connection to supernova progenitors. Surveys and data analysis also shed light on galaxy structure and evolution. Massive stars impact their environment significantly. They enrich the interstellar medium with heavy elements as they die in supernovae and trigger new star formation through feedback mechanisms. Mapping the distribution of these giants helps unravel the history of stellar assembly and chemical enrichment across galaxies, informing models of cosmic evolution. Continual improvements in computational methods, including deep learning, delta assimilation, and simulations, produce more accurate models that incorporate survey data. These models are calibrated against real observations, including discoveries like Stevenson 218, enabling predictions of stellar behavior. Understanding phenomena such as stellar winds, mass loss, and terminal stages advances when models are aligned with observational data, accelerating our grasp of complex physical processes. The discovery of Stevenson 218 exemplifies the critical role of surveys and data analytics. Infrared surveys flagged it as an extraordinary candidate based on brightness and colour signatures. Follow-up multi-wavelength observations and modelling confirmed its status as one of the largest stars, with a radius over 2,000 times that of the Sun. This success highlights the synergy of broad surveys, sophisticated data processing, and targeted follow-up, an evolving paradigm enhanced by new data and algorithms. Future projects like the Vera C. Rubin Observatory's LSST promise further breakthroughs. LSST will generate petabytes of data over 10 years, observing the entire sky repeatedly. This extensive dataset will uncover many more massive stars, revealing their variability and environments in unprecedented detail. Handling such volume demands innovative analysis techniques, such as artificial intelligence, cloud processing, and collaborative data sharing, ensuring the next wave of discoveries pushes the limits of star size, luminosity, and understanding. In conclusion, surveys and advanced data analytic methods are vital for modern stellar discovery. They allow detection, classification, and analysis of the universe's most gigantic stars, surpassing previous observational limitations. These tools not only expand catalogues of known giants like Stevenson 218, but also refine theoretical frameworks, challenge assumptions, and deepen insights into stellar life cycles. As datasets grow in size and complexity, these techniques will continue unlocking the secrets of the universe's most extreme stars, illuminating their origins, evolution, and ultimate fate. Advancements in telescope technology have revolutionized our ability to measure the dimensions of stars like Stevenson 218, bringing us closer to understanding these colossal celestial bodies with unprecedented precision. As we continue to push the boundaries of our instruments, we're uncovering details about the universe that once seemed impossible to observe. One of the most significant breakthroughs has come from larger, more powerful telescopes, both on the ground and in space. Ground-based observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii have been equipped with adaptive optics systems, an engineering marvel that compensates for Earth's atmospheric turbulence. This technology analyzes atmospheric distortions in real time and adjusts optics instantly, resulting in clearer, sharper images of distant stars. Such images allow astronomers to resolve details that would otherwise be blurred or hidden. Adaptive optics have been especially valuable for interferometry, where light from multiple telescopes is combined to mimic a larger aperture. This method effectively increases resolution, enabling scientists to measure stellar diameters with remarkable accuracy. For massive stars like Stevenson 218, often shrouded in dust and located at vast distances, high resolution is crucial. Interferometric techniques have enabled direct measurement of their angular size, how much sky they occupy, serving as a vital step in estimating their true physical dimensions. Space telescopes have also played a critical role. Without Earth's atmosphere to distort observations, instruments like the Hubble Space Telescope have achieved remarkable clarity, particularly in ultraviolet and visible wavelengths. While infrared observations often require space-based platforms due to atmospheric absorption, space telescopes remain essential for unimpeded data collection across spectra. Advanced instruments aboard these observatories, equipped with sensitive detectors and filters, enable precise measurement of stellar brightness and size, even for stars embedded in dense dust clouds. Beyond size measurements, improvements in detector sensitivity are allowing astronomers to observe minute details about stellar atmospheres and surface features. High-resolution spectrometers analyze spectral lines from a star's surface, providing indirect clues about its size, temperature, and atmospheric dynamics. When combined with interferometric data, these spectral signatures refine models and lead to more accurate stellar dimensions. A notable breakthrough has been very long baseline interferometry, VLBI. By linking radio telescopes across continents, VLBI achieves resolutions comparable to or exceeding optical telescopes in certain observations. This technique has enabled precise measurements of some of the largest stars, even those shrouded in dust and gas, by observing emissions at radio wavelengths. Combining data across different wavebands offers complementary information, helping us develop a comprehensive picture of a star's true size. Laser guide star adaptive optic systems, now common on many modern ground-based telescopes, further improve observational clarity. These systems project powerful lasers into the upper atmosphere, creating artificial guide stars as reference points for real-time atmospheric correction. This technology enhances image quality, especially when natural guide stars are scarce, such as when observing distant dust-enshrouded giants like Stevenson 2-18. In addition, advancements in detector technology have pushed the sensitivity limits, enabling detection and analysis of faint signals from distant or obscured stars. Charge-coupled devices, CCDs, and newer infrared detectors feature lower noise and higher dynamic range, allowing astronomers to capture the faint light from enormous stars even when hidden by cosmic dust. These improvements help refine measurements of stellar brightness and size, critical for calculating their physical parameters with increased accuracy. Infrared interferometry has opened new avenues for measuring stellar diameters, since many stars like Stevenson 2-18 are heavily obscured at optical wavelengths. Infrared observations penetrate dust clouds, revealing stellar surfaces that are otherwise hidden. Instruments like the Very Large Telescope Interferometer, VLTI, combine light from multiple telescopes in the infrared, producing high-resolution images. These capabilities allow astronomers not only to measure the star's size, but also to observe atmospheric variations, crucial for understanding processes like mass loss and stellar evolution at such extremes. The evolution of computational power and image processing algorithms has also contributed significantly. Techniques like aperture synthesis and deconvolution blend data from multiple observations into detailed images of stellar surfaces. These methods mitigate noise and atmospheric effects, providing clearer views of stellar disks. When combined with precise parallax data from missions like Gaia, which accurately determine stellar distances, these detailed images yield highly precise radii measurements. Looking ahead, upcoming telescopes such as the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, promise to push observational limits further. Their massive apertures, coupled with next-generation adaptive optics, are expected to resolve stellar features at unprecedented levels. Even more sensitive infrared instruments and interferometric capabilities will refine size measurements of giant stars, even at distances beyond the reach of current telescopes. Advances in artificial intelligence, AI, and machine learning are also enhancing data analysis and interpretation. These tools help process the enormous datasets generated by high-resolution observations, identifying subtle features and patterns that improve estimates of stellar sizes. AI algorithms can optimize observational strategies by selecting the best configurations for challenging, faint, or distant objects, maximizing data quality. All these technological developments together deepen our understanding of stars like Stevenson 2-18. They enable us not only to measure their sizes more precisely, but also to study their atmospheres, composition, and variability in unprecedented detail. Each breakthrough brings us closer to decoding the complex physics governing these stellar giants, shedding light on their formation, evolution, mass loss, and influence on their host galaxies. Ultimately, the relentless march of telescope technology, advances in optics, detectors, computational techniques, and observational strategies acts as a cosmic magnifying glass. It reveals the true grandeur of stars like Stevenson 2-18, uncovering their secrets and expanding our view of the universe. These improvements sharpen our perspective on the universe's most enormous and enigmatic stars, helping us unlock their mysteries and deepen our understanding of the cosmos. The formation of massive stars like Stevenson 2-18 has long fascinated astronomers, posing some of the most intriguing questions about stellar evolution and the processes that shape our universe. These stars, which can reach radii over 2,000 times that of our Sun, and possess masses exceeding 20 times that of the Sun, are born under conditions that challenge our understanding of star formation. Current theories attempt to piece together the complex tapestry of physics, from the collapse of massive clouds of gas and dust to the powerful feedback mechanisms that eventually regulate their growth. One of the leading ideas centers on the gravitational collapse of dense regions within giant molecular clouds, vast, cold assemblies of gas and dust that serve as stellar nurseries. Within these clouds, turbulence and instabilities generate regions of heightened density, creating pockets where gravity overcomes internal pressure. As these dense cores accumulate mass, they begin to contract under their own gravity, igniting the birth of a protostar. For massive stars like Stevenson 218, this process must occur rapidly, given their short formation timescales, on the order of a few 100,000 years, much faster than the more leisurely development of lower mass stars. However, forming a star with such enormous mass introduces several complexities. Unlike smaller stars, massive protostars are subject to intense radiation pressure, an outward push caused by photons streaming out from the hot, dense core. Early theories suggested that radiation pressure would effectively halt further accretion of matter once a certain luminosity was reached, preventing stars from exceeding approximately 20 times the Sun's mass. Yet, observations have revealed stars even more massive, indicating that nature finds ways to circumvent this barrier. Modern models propose that massive star formation involves a combination of mechanisms that help overcome radiation pressure. One such process is accretion through a circumstellar disk, a rotating disk of gas and dust that feeds material onto the forming star. The disk's geometry allows radiation to escape along the poles, reducing the outward forces on infalling material in the equatorial plane. This anisotropic radiation creates a safer pathway for matter to continue accreting, enabling the star to grow rapidly despite its intense luminosity. Additionally, outflows and stellar winds are thought to play a crucial role. As the protostar accumulates mass, it begins to generate powerful bipolar outflows, jets of high-velocity material ejected along its rotational axis. These outflows carve out cavities in the surrounding cloud, channels through which radiation can escape, further alleviating the resistance against infall. The feedback from these outflows can be turbulent, stirring the ambient medium and preventing the buildup of radiation pressure that would otherwise halt the star's growth. Another exciting aspect of massive star formation theories involves competitive accretion. In clustered environments, massive stars seldom form in complete isolation. Instead, they emerge from dense stellar clusters where multiple protostars vie for the available gas. In these crowded nurseries, gravitational interactions and dynamic processes lead to some protostars gaining a significant share of the gas, effectively bullying their neighbours out of the way and rapidly increasing in mass. This competitive process can produce stars as large as Stephenson 218 by drawing in extensive amounts of material from the shared reservoir. The idea of gas mergers gases has also garnered attention in explaining the origins of the most massive stars. In highly dense regions, protostars and young stars can collide and coalesce, combining their masses into a single, more massive star. Although this is a less common pathway compared to accretion, it provides a plausible route for stars to reach extraordinary sizes, especially within stellar clusters where densities can be extreme. Such mergers could help explain the presence of some of the most massive stars observed, which sometimes challenge the limits set by accretion models alone. Beyond the initial formation, the subsequent evolution of massive stars hinges on their environment and the feedback processes they generate. Their intense radiation, stellar winds, and eventual supernova explosions shape their local surroundings and influence further star formation. Interestingly, the environment of Stephenson's 218, a red supergiant, suggests it has already entered a later phase of stellar evolution. But how did it reach such an enormous size? Theories indicate that its progenitor likely started as a very massive star, possibly forming through the same processes described earlier, but with extraordinary conditions or combining mechanisms such as a prolonged accretion phase and environmental factors that sustained its growth. Magnetic fields are also believed to influence the formation of massive stars. They can channel accretion flows, help dissipate angular momentum, and contribute to the collimation of outflows. While the precise role of magnetic fields remains an active area of research, their inclusion in models has enhanced our understanding of how turbulence and magnetic forces work together to shape star formation processes. Finally, the formation of Stephenson 218 and similar stars is not only a question of how they form, but also a matter of the initial conditions that allow such massive objects to take shape. Factors like metallicity, the abundance of elements heavier than helium, influence cooling mechanisms in the gas cloud. More metals mean more efficient cooling, which can facilitate the collapse of larger, denser regions of gas. This can favour the formation of more massive stars, especially in environments rich in metals, such as the inner parts of galaxies. Studying Stephenson 2-18 provides critical insights into these processes because its extreme size and luminosity push the boundaries of current models. Theories are continuously refined as new observations emerge, especially with the advent of more powerful telescopes operating in infrared and radio wavelengths, capable of penetrating dense dust clouds and unveiling the birth environments of the most massive stars. The interplay of gravity, radiation, magnetic fields, turbulence, and stellar feedback constitutes a complex dance, one that scientists are still deciphering. In essence, the formation of such colossal stars as Stephenson 2-18 is a symphony of cosmic forces. It involves rapid gravitational collapse within turbulent molecular clouds, aided and regulated by magnetic fields, accretion disks, outflows, and environmental factors. While no single theory has yet provided a complete picture, each advances our understanding of these astonishing objects, their origins, and their remarkable journeys through stellar evolution. The study of Stephenson 2-18 and stars like it not only sheds light on the life cycles of some of the universe's most magnificent inhabitants, but also enriches our comprehensions of how the cosmos evolves on the grandest scales. The story of a star like Stephenson 2-18 is a grand saga of transformation, marked by dramatic changes driven by complex physical processes that scientists are still unraveling. These colossal stars, distinguished by their massive sizes and luminous brightness, follow a life cycle that's both powerful and fleeting on cosmic timescales. They are born from vast molecular clouds of gas and dust, where gravity pulls material together, igniting nuclear fusion in their cores. This process lights up their enormous surfaces and sets them on a path that, despite their size and brightness, is transitory compared to the universe itself. Initially, Stephenson 2-18 emerges as a hot, dense core within a swirling cloud of gas. As it accumulates mass, the nuclear furnace inside it ignites, converting hydrogen into helium and releasing enormous energy. This phase, the main sequence, is where stars spend much of their lives, burning brightly and steadily. Given their size and mass, stars like Stephenson 2-18 are at the upper end of the stellar mass spectrum, and this phase is relatively brief in cosmic terms, lasting only a few million years. During this period, the star is stable, shining intensely but gradually turning its fuel into heavier elements via nuclear fusion. As the hydrogen core gets depleted, the star's internal balance shifts. Gravity begins to outweigh radiation pressure, causing the core to contract and heat further. This contraction ignites a new phase, where the outer layers expand dramatically, transforming the star into a supergiant, a huge, luminous object that can be hundreds or more than 1,000 times the Sun's radius. For stars like Stephenson 2-18, this stage involves powerful stellar winds that strip away their outer layers, revealing turbulent interior processes. These winds, driven by the star's intense radiation and convection currents, carry particles into space. The star's atmosphere becomes increasingly unstable with age, pulsating and varying in brightness, phenomena observed in many red supergiants. These pulsations are driven by complex oscillations within the star's interior, resonances that cause the star to expand and contract rhythmically. The variability of Stephenson 2-18, with its enormous size and luminous output, signals this turbulent phase. During this time, it loses mass at an extraordinary rate, millions of times the Sun's mass loss, through powerful stellar winds. These winds carry away outer layers, enriching the surrounding interstellar medium with heavy elements and dust, which contribute to the formation of new stars and planets elsewhere. After millions of years, this turbulent existence nears its end. The core, heavily processed with elements like helium, carbon, and oxygen, continues contracting under gravity. When the core reaches a critical density and temperature, nuclear fusion can no longer support the outer layers. Catastrophic events then unfold. The core collapses inward, while the outer layers are expelled in a supernova explosion. For stars like Stephenson 2-18, their enormous initial mass makes a supernova, or even hypernova, the likely fate. leaving behind a neutron star or, if massive enough, collapsing into a black hole. This explosive death is among the most luminous and energetic events in the universe, often outshining entire galaxies for a brief period. The explosion disperses processed elements into space, seeding future generations of stars and planets. The aftermath may be a supernova remnant, a glowing shell of gas and dust that continues to shine for tens of thousands of years, visible across vast distances. The core becomes an ultra-dense object, either a neutron star or black hole, testament to the star's violent end. The evolution of stars like Stephenson 218 encapsulates the cosmic cycle of birth, life, and death. These titanic stars are not only awe-inspiring astrophysical phenomena, but also vital to galactic evolution. They forge heavier elements necessary for planet formation and complex chemistry, even life. Their lifespans are only a few million years, just a brief window in cosmic time, yet their influence is profound, affecting generations of stars and shaping the galaxy's fabric. Advances in astrophysics, especially infrared observations and sophisticated stellar atmosphere models, help shed light on these giant objects. Researchers study pulsations, spectra, and mass loss rates to deepen understanding of their evolution. Yet, the pathways of stars like Stephenson 2-18 remain subjects of active investigation, as scientists work to refine models that account for their enormous sizes, variability, and final fates. Recent discoveries of supermassive giants challenge previous ideas about stellar growth limits. Stephenson 2-18's enormous radius, more than 2,000 times the Sun's, operates at the edge of stellar stability. Its existence raises questions about mechanisms regulating growth and limits to stellar mass. Understanding these boundaries informs stellar physics and the conditions that facilitate such extreme stars. Beyond their dramatic deaths, stars like Stephenson 2-18 inform astronomers about early universe conditions and galaxy evolution over billions of years. Their explosive deaths release heavy elements, enabling the formation of new stars, planets, and possibly life. This cycle highlights interconnected cosmic phenomena. The life of a massive star influences galaxy evolution. Future telescopes and observational techniques will aim to catch early stages of stars like Stephenson 2-18, observe their pulsations in greater detail, and more precisely determine their masses and compositions. These insights will refine our understanding of their life cycle, from fiery birth to catastrophic end, and help explain how they shape the universe's grand design. The life cycle of a star like Stephenson 2-18 is a fiery, turbulent journey, a testament to the raw power of fundamental forces. Despite their brief existence in cosmic terms, their legacy resonates across the universe, contributing to matter, energy, and the ongoing story of stellar evolution. Their existence showcases the universe's capacity for both extraordinary creation and destruction, a continual cycle of renewal driving cosmic progress. The journey of red supergiants and hypergiants is a spectacular saga, a testament to the grandeur and brutality of stellar evolution at its most extreme. These giants begin life as massive stars born from dense molecular clouds, the sprawling cradles of star formation where gravity causes clouds of gas and dust to collapse, igniting nuclear fusion in their cores. Their early stages are marked by rapid growth and energetic activity, but it is as they enter the later portions of their lives that their evolution becomes truly remarkable. Initially, after formation, these stars spend millions of years fusing hydrogen to helium in their cores, a phase called the main sequence. Due to their immense masses, often exceeding 20 times that of the Sun, they burn brightly and intensely, radiating vast amounts of energy. However, this phase, though critical, is relatively short on cosmic timescales. They quickly exhaust their core hydrogen fuel, beginning a complex, multi-stage journey through evolved phases. As hydrogen runs out in the core, fusion shifts to a shell surrounding a contracting core composed of inert helium. This causes the outer layers to expand dramatically, transforming the star into a red supergiant or hypergiant. During this expansion, the star's radius can balloon to thousands or over 2,000 times that of the Sun, making these stars some of the most enormous objects in the universe. Their surface temperatures drop compared to earlier, hotter blue or yellow phases, giving them the deep reddish appearance that earns their name. In this expanded state, the stars become unstable, engaging in intense pulsations and mass loss. Their atmospheres are riddled with convection currents, voluminous, rising boiling-like motions akin to boiling water, but on a cosmic scale, leading to enormous convective cells. These processes, coupled with radiation pressure, drive significant material away from the star's surface. Stellar winds become ferocious, creating a dense, dusty shroud around the star as it sheds outer layers. These winds can reach speeds of hundreds of kilometers per second, carrying away several solar masses over thousands or tens of thousands of years, an enormous amount for such a relatively brief phase of stellar evolution. As the star continues evolving, it begins fusing heavier elements, moving from helium to carbon, neon, oxygen, and beyond, in successive shells around the core. The star's internal structure becomes increasingly complex, with multiple burning shells layered within. The outer envelope, laden with mass loss, becomes more extended and unstable. Its luminosity nears the Eddington limit, where radiation pressure counteracts gravity, further contributing to instability and mass ejection episodes. These advanced phases are inherently unstable and may last only a few 100,000 to a few million years, during which the star exhibits signs of dramatic variability. Brightness fluctuations, irregular pulsations, and episodic outbursts are common. Hypergiants are known for their chaotic atmospheres, with large-scale eruptions ejecting material into space. These episodic mass loss events sometimes resemble stellar volcanoes, where layers are expelled in luminous outbursts, enriching the surrounding space with heavy elements. Eventually, these stars approach the end of their lives, with internal fusion reactions preparing for a catastrophic finale. The inert core continues contracting and heating, fusing elements heavier than oxygen in the most advanced stages. The core reaches a critical threshold, around 1.5 to 2 solar masses compressed into a tiny volume, becoming unstable and collapsing under gravity. This core collapse triggers a supernova explosion, often classified as a Type II supernova, one of the universe's most energetic events. This explosion signifies the star's death, its final violent release of energy, blowing off layers built over millions of years. The shockwave propagates outward, sweeping through the surrounding interstellar medium, compressing gas clouds and seeding space with heavy elements forged inside the star. The remnants leave behind a compact object, a neutron star, or, if the star was massive enough, a black hole. These remnants are among the densest objects in the universe, the crystalline cores of stars that have undergone violent demise. For some of the most massive hypergiants, the story may differ slightly. Their enormous mass sometimes enables them to bypass the typical supernova route, collapsing directly into a black hole with minimal outward display. Alternatively, if the star loses enough mass through strong stellar winds and eruptions during its lifetime, it might explode as a different type of supernova or quietly fade away as the core collapses into a black hole with little surface indication of internal chaos. Throughout this evolution, red supergiants and hypergiants are prolific factories of heavy elements. Their intense winds and explosive death scatter these elements into the galaxy, enriching the interstellar medium and providing raw material for future stars, planets, and life's building blocks. They influence galaxy evolution by affecting star formation and galactic dynamics through feedback processes. What makes this path particularly fascinating is its brevity and chaos relative to the star's initial stable stages. A star may spend millions of years as a stable, luminous main sequence beacon, but the final acts, pulsations, eruptions, and explosions, occur over a few 100,000 years or less. This fleeting nature emphasizes the importance of population studies and direct observations, as catching a star in these final phases is like witnessing a cosmic fireworks display, escalating rapidly before fading or transforming into a spectacular explosion. The complexity of these stages highlights the delicate force balance, gravity trying to crack the star apart versus radiation pressure pushing outward. Studies of stars like Stephenson 218 reveal how dynamic and volatile these giants are nearing the end of their lives. Their evolution underscores a broader astrophysical truth, that the most massive luminous stars are both creators and destroyers, contributors to the universe's chemical diversity, but ultimately destined for a spectacular demise that reshapes the cosmic landscape. As we explore these giants' life cycle, they remind us that even seemingly stable and enduring objects are transient. Their evolution epitomizes the cycle of birth, death, and rebirth, driving the universe's dynamic and ever-changing tapestry. Stevenson 2-18, as the largest star discovered, embodies this continuum, its enormous size and volatile life, echoing the grandeur of stellar evolution at its most extreme, providing astronomers a rare glimpse into the final fiery chapters of a star's life. The story of a star as colossal as Stephenson 2-18 isn't just about its size and luminosity, but also about the relentless processes shaping its destiny, mass loss and stellar winds. These phenomena aren't minor details, they are fundamental forces influencing how such gigantic stars live, evolve, and meet their end. Imagine a star so vast that its surface is hundreds of times farther from its core than Earth is from the Sun. Its outer layers are held in delicate balance, thousands of times more tenuous than those of smaller stars. This fragility makes it especially susceptible to stellar winds, powerful streams of charged particles ejected from its surface at thousands of kilometers per second. These winds act like a star's breath, gradually carrying away material into space. Though subtle over human timescales, over thousands to millions of years, they profoundly alter the star's mass, composition, and fate. Mass loss from these stars begins to play a pivotal role in their life cycle because it directly influences their structure and internal processes. A star's evolution depends critically on how much fuel remains in its core, which depends on its initial mass and how quickly it sheds that mass. For a luminous star like Stephenson 2-18, these winds are not just a trickle, they're a deluge, shedding hundreds of solar masses over its lifetime, peeling away outer layers endlessly. When a star loses mass through stellar winds, its core is affected in complex ways. The core continues nuclear fusion, converting hydrogen to helium and heavier elements like carbon and oxygen. But as outer layers are blown away, the star's gravitational grip weakens, causing slight contraction and increasing core temperature and pressure, which accelerates fusion. This creates a feedback loop where increased fusion boosts luminosity and intensifies winds, further stripping the outer envelope. In some cases, this mass loss causes the star to transition through different evolutionary phases faster. For Stephenson 2-18, in its late red supergiant phase, ongoing mass loss is critical. The star exists in a state of equilibrium, with inflated, tenuous outer layers. As stellar winds carry away this material, the star's envelope thins and cools while the core grows hotter and denser. This process eventually destabilizes the star, bringing it closer to collapse. As the star loses enough mass, its core becomes unstable to gravitational collapse. It can no longer maintain hydrostatic equilibrium. Pressure outward balances gravity inward. Reduced mass weakens the outer layer's gravitational binding, making it easier for the core to collapse suddenly in a supernova explosion. Thus, stellar winds and mass loss determine whether the star will quietly shed outer layers and end as a neutron star or black hole or explode in a violent supernova. Beyond its death, stellar winds influence the surrounding environment. Material expelled enriches the interstellar medium with heavy elements forged in the core, such as carbon, nitrogen, oxygen, and metals. These elements return to the galaxy, becoming raw materials for new stars, planets, and perhaps life. Stephenson 2-18 isn't just an endpoint, but a vital contributor to the cosmic cycle of matter. Stellar winds also modify the star's immediate environment, creating vast circumstellar shells of gas and dust. These aren't static, they pulse and ripple, affected by variable brightness and bursty mass ejections. The interplay often forms spectacular nebulae illuminated by reflected light or energized by shock waves from wind collisions. Observing these shells gives astronomers insight into the star's recent mass loss history, revealing how dynamic and chaotic a red supergiant's life really is. In stellar evolution models, the rate and nature of mass loss remain some of the greatest uncertainties. For massive stars like Stephenson 2-18, small differences in wind strength or observational data can drastically influence predictions about how much mass remains at supernova time and the kind of remnant left. Will it be a black hole or neutron star? Will the explosion be a gamma-ray burst or a more subdued event? These questions hinge on understanding how effectively the star loses its mass, a puzzle still unresolved. The mechanisms driving these winds are complex. They arise from several factors: the star's immense luminosity pushing outward, radiation pressure on ions and dust grains, magnetic field interactions and pulsations that send shock waves into the atmosphere. dust formation plays an especially important role in red supergiants like Stephenson 2018. As the outer atmosphere cools and molecules condense into dust, radiation pressure propels dust outward, dragging gas along. This process efficiently removes mass and shapes the circumstellar environment into asymmetric structures detected through infrared and radio telescopes. Stellar winds have significant observational consequences. Dense shells of ejected material can obscure, redden, or distort light from the star, complicating measurements of size and temperature. Over time, as winds carry away mass, the star's spectral signature evolves, providing clues about wind changes and composition. These signatures are critical for refining stellar models, helping scientists understand not just Stephenson 2-18 but stars across the universe. Mass loss and stellar winds act as both sculptors and storytellers in cosmic evolution. They carve the star's future, deciding if it ends in a supernova or fades quietly into a dense remnant. Simultaneously, they distribute elements forged deep within, fueling a matter cycle that underpins galaxy evolution and planetary formation. These processes also reflect the interconnectedness of cosmic phenomena. The vigor of a star's winds is linked to its initial mass, composition, rotation, magnetic fields, and environment. Deciphering this interplay in stars of such extreme size pushes astrophysics forward, demanding increasingly sophisticated observations and theories. Stephenson 2-18's prodigious mass loss and intense winds make it a natural laboratory for extreme astrophysics. Studying it offers valuable insights into high-mass stellar evolution, supernova formation, and black hole origins. It prompts reflection on how life cycles are driven not just by initial properties, but also ongoing interactions with surroundings, an ongoing dialogue between a star and the cosmos it helps shape. As Stephenson 2-18 continues shedding its outer layers, it writes the final chapters of its grand stellar saga: energized winds, transformation, and renewal. The story isn't merely about moving material into space, but about cosmic renewal, the evolving universe's most massive stars, and the rich cycle of creation that extends beyond any single star's life. Studying Stephenson 2-18 provides critical insights into the extreme conditions and phenomena shaping the life cycles of the most massive stars. As the largest star ever discovered, its size, luminosity, and evolutionary stage offer valuable data that expand our understanding of stellar physics. Analyzing this colossal red supergiant allows astronomers to refine models of stellar structure, mass loss, and evolution, impacting multiple areas of astrophysics. One major contribution of Stephenson 2-18 is its influence on understanding stellar atmospheres and envelopes in massive stars. Red supergiants like it have outer layers that are both enormous and highly dynamic. They show turbulent convection, powerful stellar winds, and episodic mass ejections affecting their evolution and final fate. By studying its temperature, spectral features, and variability, scientists develop better models for energy transport, mass loss, and environmental interaction. This challenges and refines knowledge of convection under extreme gravity and radiation pressure at colossal scales. Furthermore, Stephenson 2-18's size and luminosity challenge existing notions of the Eddington limit, the balance point where radiation pressure counters gravity. Observations of how it sustains such an enormous size without dispersing shed light on radiation hydrodynamics in dense stellar conditions. Understanding how opacity and the interplay of ions and electrons function under these extreme environments improves stellar evolution models, especially for stars nearing their end stages. The star's characteristics serve as benchmarks for calibrating evolutionary tracks of massive stars' late phases. These models rely heavily on initial mass, chemical composition, rotation, and mass loss rates. Stephenson 2-18's observed parameters, radius, luminosity, surface gravity, spectral features, provide empirical data to confirm or challenge theoretical assumptions. Its extreme size suggests rapid, significant mass loss, a key factor influencing the transition into supernovae. Improving understanding of mass loss mechanisms allows for more accurate predictions of supernova progenitors. Additionally, Stephenson 2-18 offers a natural laboratory for exploring the end-of-life scenarios for massive stars. Its advanced evolutionary stage suggests it is nearing a supernova. Studying its internal structure, outer layer composition, and mass loss history helps predict the type of supernova it might produce and the nature of its remnant, neutron star or black hole. These insights have broader implications for supernova rates, galactic chemical enrichment, and formation of compact objects. Its immense size and brightness also offer a testing ground for supernova physics and remnant interactions with circumstellar material. When it eventually explodes, the supernova's brightness, spectral evolution, and remnant features will be shaped by its prior mass loss. Observing and modelling these processes deepen knowledge of supernova mechanisms, energy release, and nucleosynthesis. This contributes to understanding the chemical evolution of galaxies over cosmic time. Technologically, the challenges of observing Stephenson 2-18 have driven advances in astronomy. Its brightness and size require sophisticated instruments like infrared interferometry and high-resolution spectroscopy to resolve surface features and atmospheric dynamics. These innovations improve the ability to image stellar surfaces, study surface granulation, and measure oscillations in massive stars. Such techniques are applicable to other distant, challenging objects, broadening stellar research capabilities. Studies of Stephenson 2-18 also improve understanding of variability in red supergiants. Its complex pulsation patterns, surface brightness fluctuations, and episodic mass ejections impact evolution and fate. Recognizing these phenomena helps explain the physical mechanisms driving variability, the timescales involved, and their influence on mass loss rates. This enables more comprehensive models of massive star evolution, especially concerning how they shed outer layers before exploding. A key aspect is the evolutionary connection between massive stars and their supernova progenitors. Stephenson 2-18's attributes help define initial conditions for different supernova pathways. Whether a red supergiant ends as a Type 2P or Isoswell supernova depends heavily on mass loss and core properties. Precise measurements of its current state provide data to constrain thresholds and physical processes involved, refining predictions of supernova outcomes. Studying such extreme stars also enhances understanding of cosmic chemical enrichment. When Stephenson 2-18 explodes, it disperses heavy elements like iron, nickel, and alpha elements, enriching surrounding space. Comprehending its initial composition, internal element processing, and explosion nature allows better modelling of nucleosynthetic yields. This knowledge contributes to understanding galaxy formation, evolution, and the distribution of life-essential elements. On a larger scale, Stephenson 2-18 serves as a benchmark for interpreting distant galaxy populations. Its properties inform models of integrated stellar light, aiding the analysis of unresolved stellar populations. Understanding the spectral and luminosity contributions of stars like it helps decipher galaxy star formation histories, ages, and metallicities, particularly important when direct stellar observation isn't possible. Discoveries about Stephenson 2-18 challenge existing theories on the upper limits of stellar size and mass. Pushing observational boundaries to include such stars compels revisions of models regarding stellar formation and stability. These updates are crucial for understanding how stars form in extreme environments, how they sustain structural integrity under intense gravity, and how they avoid collapse or disruption. These constraints are vital for accurate stellar physics under extreme conditions. In astrophysics, images and spectra from Stephenson 2-18 help improve models of stellar atmospheres where traditional assumptions, like hydrostatic equilibrium, fail. Its extended pulsating atmosphere, prone to large-scale ejections, necessitates dynamic modelling. Integrating observational data with hydrodynamic simulations results in more realistic approaches that capture the observed complexity. Such models are essential for interpreting other evolved stars and understanding their variability. Studying Stephenson 2-18 also deepens appreciation for the interconnectedness of cosmic phenomena. Its evolution, from formation in star-forming regions to its giant phase to potential explosion, is a key piece in cosmic evolution. Each insight informs disciplines from matter physics under extreme conditions to galaxy evolution and the universe's large-scale structure. Its life cycle illustrates how understanding extraordinary objects unlocks fundamental cosmic principles. In summary, Stephenson 2-18 is more than just an enormous star. It functions as a cosmic laboratory, testing the limits of our understanding. It drives technological innovation, enhances models across astrophysics, and illuminates fundamental processes shaping the universe. Its study refines theories, challenges assumptions, and broadens the horizons of stellar physics, with impacts across the entire field. The star's very existence underscores the universe's diversity and extremes, inspiring ongoing exploration and discovery at the frontiers of science. Stephenson 2-18 is a remarkable star, not just for its size but because of what it reveals about the lives of the most massive stars. Its enormous dimensions and luminosity serve as a window into the turbulent processes that govern the birth, evolution, and fate of these giants. Understanding Stephenson 2-18's significance is tied to the life cycle of massive stars, which spans millions of years, brief in cosmic terms but filled with rapid change, fierce winds, and dramatic transformations. Studying such a colossal star offers insights into how stars remain stable during their fiery youth, shed their outer layers in their final stages, and influence the cosmos. Massive stars form from dense molecular clouds, where gravity causes gas and dust to collapse. Stephenson 2-18 hints at the processes that determine the late stages of stellar life, how these titans grow and lose mass before their explosive end. Its radius, nearly 17 times that of the Sun, and its luminosity, outshining hundreds of thousands of stars, indicate a core burning through hydrogen at a staggering rate. This rapid fusion creates heavier elements, leading to layered structures within the star as advanced fusion stages are reached. What makes Stephenson 2-18 particularly insightful is how it exemplifies intense mass loss phenomena characteristic of supergiant stars' final phases. These stars are not stable, but pulsate with stellar winds, powerful streams driven by radiation from hot, luminous surfaces. The star's vast size amplifies these winds, causing significant mass loss over short cosmic timescales. Observations show that such stars can lose a large fraction of their mass in decades, a blink in cosmic time, affecting their evolutionary path. This loss influences whether they will explode as supernova, leave behind neutron stars, or form black holes. The star's late evolutionary stage, marked by its size and instability, provides key insights into how mass loss rates affect lifespan and death. As it continues evolving rapidly, it likely pulsates, varies in brightness, and experiences episodes of enhanced mass loss that ripple through its outer layers. These pulsations are driven by radiation pressure and gravity, causing rhythmic expansions and contractions. Such phenomena impact the star's internal physics and serve as observable signals for astronomers, allowing tracking of its development. A fundamental aspect of Stephenson 2-18's evolution concerns metallicity, elements heavier than helium. Its spectral features suggest a metal-rich composition, influencing wind dynamics. Higher metallicity increases line absorption capacity, boosting radiation-driven winds. Studying stars like Stephenson 2-18 helps us understand how metal content impacts mass loss rates, which in turn affects the star's remaining lifespan and the nature of its end. Mass loss also shapes the star's environment. The intense winds create complex circumstellar surroundings rich in dust and molecules. These dusty shells, illuminated by stellar radiation, appear as infrared excesses, indicating ongoing mass ejection. Over time, these shells expand and disperse, enriching the interstellar medium with heavy elements. This material contributes to the formation of future stars and planets, linking stellar death to galactic evolution. Infrared observations reveal thick dust and gas layers from recent mass loss episodes, offering insights into the star's ongoing instability. As it sheds outer layers, it enters a critical phase where further instability and mass ejection prepare it for its ultimate fate. These ejections strip the star down to its core, setting the stage for a supernova. The star's final explosion depends on its mass, core composition, and remaining hydrogen layers. With its immense size, Stephenson 2-18 is likely nearing this spectacular end. As its core becomes denser and hotter, nuclear fusion progresses through heavier elements until it produces iron, a dead end for fusion energy, as fusing iron consumes energy. When enough iron accumulates, the core can no longer support gravity, triggering a core collapse supernova. This explosive event disperses the star's outer layers at incredible speeds, scattering the enriched materials produced during its lifetime. The supernova remnant seeds the galaxy with heavy elements like iron, nickel, silicon, vital for planet formation and life. This process exemplifies the interconnected cycle of stellar death, chemical enrichment, and galactic evolution. The remnants often form dense, compact objects, neutron stars or black holes, carrying the legacy of their violent birth. Studying Stephenson 218 offers critical data to refine stellar evolution models. Precise measurements of its size, luminosity, and mass loss rates help clarify how such enormous stars develop. These data help decode feedback mechanisms, stellar winds, pulsations, magnetic fields that influence a star's lifespan and demise. Understanding why some stars produce neutron stars and others black holes depends on this knowledge. Furthermore, Stephenson 218 serves as a natural laboratory for physics under extreme conditions, high temperatures, densities, and radiation pressures, challenging assumptions in nuclear physics, plasma physics, and radiative transfer. Observations of its behavior inform these fields and deepen our understanding of energetic cosmic phenomena. As a luminous red supergiant, Stephenson 218 also acts as a benchmark for understanding massive stars across different contexts, early universe stars, distant galaxies, and at various stages of galactic development. Its study helps illuminate how the most massive stars influence their environments, through feedback, chemical enrichment, and triggering or suppressing new star formation. In sum, Stephenson 218 is more than a colossal star. It narrates the complex saga of stellar evolution for the universe's giants. Its physical properties, mass loss behavior, and evolutionary stage offer invaluable insights into the lives and deaths of massive stars. These observations fill pieces of a cosmic puzzle, revealing how energetic stars live, die, and shape their surroundings. Each study of Stephenson 218 brings us closer to understanding the universal principles underlying the life cycle of the universe's most massive and luminous celestial entities. Stephenson 218 stands as an extraordinary cosmic laboratory, offering insights that can significantly refine our understanding of stellar evolution, especially for the most massive stars. As the largest known red supergiant, its immense size, luminosity, and physical properties challenge and expand existing models, prompting us to revisit theories on how such colossal stars live and die. One primary way Stephenson 218 can improve stellar evolution models is through its size and structure. Traditional models predict massive stars gradually transform over millions of years, with their outer layers expanding and cooling during the supergiant phase. However, the exact size limits during this phase remain uncertain, especially near the upper bounds of stability. By providing a precise measurement of Stephenson 218's radius, estimated to be over 1,000 times that of the Sun, astronomers can test how current models predict the maximum size of red supergiants. This informs theories about how stellar material behaves under extreme conditions, such as high luminosity and low surface gravity, and constraints on when and how such enormous stars become unstable. Additionally, studying Stephenson 218's luminosity and temperature reveals internal processes governing energy production and transport. Its brightness, surpassing thousands of suns, indicates a highly luminous interior powered by nuclear fusion. Observations show these stars have complex convective envelopes, with turbulent flows in their outer layers. Analyzing spectral features and variability provides clues about convection operating under extreme circumstances. These observations enable astrophysicists to refine models of energy transfer within massive stars, especially regarding how radiation and convection balance, influencing pulsations and stability. Beyond internal structure, Stephenson 218 offers valuable data on mass loss mechanisms in late stellar evolution stages. Massive stars like it lose significant outer layers through stellar winds, boosted by radiation pressure. Despite decades of study, the drivers and rates of mass loss near supernova stages remain elusive. Spectral signatures of stellar winds, dust formation, and outflow velocities help researchers understand the physical conditions causing mass ejection. This knowledge refines empirical and theoretical prescriptions used to estimate mass loss over a star's lifetime, which critically impacts its ultimate fate. Understanding mass loss is fundamental because it influences how these stars evolve toward their endpoints, whether becoming neutron stars or black holes after supernova. The current mass and evolutionary path are shaped by material shed. If models underestimate wind strengths, they might inaccurately predict core mass at collapse, leading to errors in remnant predictions. Precise measurements from Stephenson 2-18 enable astronomers to recalibrate these models, ensuring they reflect the realities of extreme mass loss rates. Coinciding with its advanced age and stage, Stephenson 2-18 exemplifies the pre-supernova phase of a massive star. Studying such stars provides crucial clues about final evolutionary stages. Its surface chemical composition reveals internal mixing processes, convection, and rotational effects that bring fusion products from the core to the surface. These surface abundances influence opacity and energy transfer, affecting overall evolution. Analyzing spectra for unusual chemical signatures helps validate or adjust theories about internal mixing, core evolution, and the time frame leading to core collapse. Moreover, Stephenson 2-18 informs our understanding of supernova progenitors. Its properties help constrain explosion models, since the star's mass, composition, and structure impact the resulting supernova's brightness, spectrum, and remnants. As an extreme supergiant nearing the end of its life, it acts as a benchmark for simulations predicting supernova characteristics, including neutrino flux, explosion energy, and nucleosynthesis yields, enhancing our grasp of these catastrophic events. Another key contribution involves the star's pulsation behavior and variability. Many supergiants exhibit irregular brightness changes caused by outer layer oscillations. Observing and modeling these pulsations enables probing of the star's internal structure. Documenting Stephenson 2-18's variability helps match observations to pulsation models, refining theories on how large, low-surface gravity stars oscillate. This improves understanding of the physical mechanisms driving stellar oscillations in supergiants, crucial for interpreting variable star data. Furthermore, Stephenson 2-18's environment and interaction with surrounding interstellar medium offer insights into galactic feedback processes. Its stellar winds and eventual supernova will inject energy and enriched material into the galaxy, influencing future star formation. Tracking how the star enriches its surroundings, including dust and heavy elements, helps model chemical evolution within galaxies. Quantifying its mass loss rate and feedback effects advances simulations of how massive stars shape their galactic neighborhoods over cosmic timescales. The star's extreme luminosity and size also serve as constraints for opacity and radiative transfer models in stellar atmospheres. Discrepancies between theoretical predictions and observations of Stephenson 2-18's spectral energy distribution challenge assumptions underlying these models. When models successfully replicate the spectral features of such giants, confidence in the physical parameters increases. Conversely, mismatches highlight areas for refinement, ultimately leading to more accurate models for massive stars in diverse environments. Finally, Stephenson 2-18 acts as a calibrator for the initial mass function, an important concept describing the distribution of stellar masses at birth in galaxies. Understanding this extreme star's evolution and properties helps interpret populations of supergiants, especially in distant or crowded regions where direct counting is difficult. This influences broader models of galaxy evolution, star formation rates, and the life cycle of stellar populations. Overall, Stephenson 2-18 is more than an extraordinary celestial object. It functions as a natural laboratory, pushing the boundaries of our knowledge about massive star life cycles. Its extreme parameters test the limits of existing theories, revealing gaps and guiding improvements. Continued observation and analysis will help refine the laws governing stellar structure, stability, mass loss, and death, enriching our understanding from star birth to supernova and beyond. Modelling stars like Stephenson 2-18 presents extraordinary challenges that push the boundaries of our understanding of stellar physics and computational modelling. These stellar giants are at the extreme end of the size, luminosity, and mass spectrum, making their behaviour complex, unpredictable, and difficult to capture precisely through simulations. Understanding their life cycles requires insight into multifaceted physical processes occurring simultaneously in their extensive dynamic atmospheres. One fundamental hurdle is the star's immense scale. Stars like Stephenson 2-18 can have radii hundreds to thousands of times larger than the Sun. This enormous size means their atmospheres are vastly extended, with regions where temperature, pressure, and density vary dramatically over short distances. Modelling such environments involves solving hydrodynamics or magnetohydrodynamics equations across large spatial domains. The steep gradients in physical properties demand extremely high resolution in simulations to accurately capture phenomena like convection, pulsations, and shock formations, which are more pronounced in these stars. Adding to this complexity are convection effects in the stellar atmosphere. In red supergiants like Stevenson 218, convection occurs over enormous scales, involving huge convective cells that can span significant fractions of the star's radius. These convection patterns are turbulent and stochastic, making them challenging to model. Numerical simulations need to incorporate turbulent convection with high fidelity, a computationally demanding task. Capturing the interplay between convection and pulsations, oscillations of the star's outer layers, requires sophisticated models and can introduce uncertainties, especially since turbulence occurs at scales below current model resolutions. The star's atmospheric dynamics also pose major challenges. Red supergiants have thick extended atmospheres driven by intense stellar winds that carry away large amounts of mass over their lifetimes. This influences their evolution, luminosity, and fate. Modelling stellar winds involves understanding processes like radiation pressure on dust and molecules that accelerate outflows, how magnetic fields may influence wind structures, and how shocks propagate through tenuous outer layers. These processes are difficult to simulate precisely because they involve non-local thermodynamic equilibrium, non-LTE effects, complex chemistry, and dust formation. Dust formation in outflows introduces additional complexity. In evolved stars like Stephenson 218, dust condenses in stellar winds, creating obscuring layers that influence radiative transfer within the atmosphere. Accurate modelling requires coupling chemical networks with radiative transfer equations. Dust not only affects observable spectral features, but also impacts the star's mass loss rates. Since mass loss governs the star's evolution, determining how fast it sheds outer layers, uncertainties in dust physics translate into uncertainties in evolutionary predictions. Thermodynamics inside such massive stars also pose challenges. Core temperatures reach hundreds of millions of degrees, with nuclear fusion processes operating rapidly, creating complex reactions and energy generation rates that vary with depth. Accurately simulating the interior involves solving stellar structure equations, including hydrostatic equilibrium, energy transport, and nuclear reaction networks. However, in massive supergiants, the outer layers are loosely bound, and turbulent convection can disrupt stability assumptions used in classical models. Furthermore, late evolutionary stages are characterized by rapid, often chaotic changes. As mass is lost, internal instabilities may lead to pulsations, eruptions, or episodic outbursts. Predicting these phenomena is difficult because they depend on small timescale processes relative to the star's lifespan, but can have significant observational effects. Simulating such transient phenomena requires detailed physics and long-term, high-resolution models that can track stellar behavior over many years or centuries in model time. Magnetic fields add another layer of complexity. While their strength in red supergiants is still under investigation, magnetic activity can influence mass loss, wind shaping, and surface phenomena. Including magnetohydrodynamics complicates models because magnetic fields need to be resolved spatially and temporally, and their interactions with plasma can lead to phenomena like collimated jets or large surface spots, further complicating observational interpretation. Uncertainties and limitations in physical inputs also hinder modelling efforts. Stellar models depend heavily on opacities, how transparent or opaque stellar material is, and nuclear reaction rates, which are often poorly constrained under extreme conditions. Small variations in these inputs can lead to large divergences in predicted properties over time. For example, slight changes in opacity can alter temperature gradients, affecting the star's size, luminosity, and mass loss rate predictions. Observational constraints further challenge modelling. Distant luminous objects like Stephenson 218 are difficult to measure directly regarding internal processes. Instead, astronomers rely on spectral data, interferometry, and light curves, each with their own uncertainties. These observations serve as benchmarks for models, but require interpretation, interpolation, or extrapolation of physical conditions, adding further inaccuracies to the modelling efforts. Computational power has historically been a limitation in simulating stars of this scale. Fully three-dimensional, time-dependent simulations that incorporate all relevant physics, hydrodynamics, radiative transfer, dust physics, magnetic fields, nuclear reactions are highly demanding. Although computational capacity has grown, models often need simplifications or approximations to be manageable. These simplifications may miss subtle physical phenomena critical for accurate modelling. The long timescales of stellar evolution stretch modelling capabilities. While some phenomena can be simulated over short periods, understanding the entire life cycle requires bridging from formation to end stages, an enormous computational and conceptual challenge. Because we observe only snapshots in their evolution, models often rely on assumptions, parameterizations, or extrapolations from better understood systems, introducing uncertainties. In essence, modelling colossal stars like Stephenson 2-18 resembles recreating a constantly changing, turbulent, layered system at the edge of current scientific and computational limits. Their vast atmospheres, turbulent convection, complex wind physics, dust formation, magnetic activity, and rapid late-life changes form a tangled web of physical processes. Each element, if not accurately represented, distances models from reality. As we push the boundaries, models become more complex and computationally intensive. Progress depends on improved physics inputs, more precise measurements of opacities, nuclear reactions, magnetic interactions, and dust physics, alongside advances in computational techniques and hardware. Innovative modelling strategies that efficiently capture essential phenomena without overburdening computational resources are crucial. These developments will enable better simulations of the inner workings of these giants, unveiling the fundamental physics behind their grandeur. Until then, their modelling remains a frontier of stellar astrophysics, challenging, fascinating, and crucial for understanding the universe's most enormous stars. 943 words. Understanding the significance of Stephenson 2-18 extends beyond recognizing it as a colossal stellar object. It acts as a beacon illuminating our galaxy's history, structure, and evolution. This star, by its size, luminosity, and unique properties, offers critical insights into the life cycle of the most massive stars and their role within the Milky Way's complex tapestry. At its core, Stephenson 2-18 highlights the diverse, dynamic stellar populations that compose our galaxy. The Milky Way isn't just a flat disk of stars, gas, and dust. It's a vibrant, evolving system with stars at various stages, from star-forming nurseries to ancient remnants. Massive stars like Stephenson 2-18 represent a key phase in this process. Their presence, life cycle, and demise influence the galaxy's chemical makeup, shaping future star and planetary systems. The discovery of Stephenson 2-18 challenges and refines our understanding of star formation and stellar evolution, especially at the upper mass limits. Such an enormous star must have formed in highly intense conditions, where gases collapse under gravity to create objects of unprecedented scale. Its existence pushes models, compelling astrophysicists to examine how such massive stars form in crowded environments like spiral arms. These regions, filled with molecular clouds, the stellar nurseries, pose questions about how a star can grow so large. Understanding how Stephenson 2-18 assembled its mass directly informs models of galactic evolution, star cluster dynamics, and the conditions necessary for forming the galaxy's most massive objects. Furthermore, Stephenson 2-18 helps map the distribution of massive stars across the Milky Way. Studying its location allows astronomers to infer properties of the galactic regions where giants like it form. Are these stars concentrated in specific arms or starburst regions? Do their positions reflect the galaxy's gravitational potential or the distribution of dense molecular clouds? These questions help visualize how the galaxy's structure influences stellar birth and evolution, revealing mechanisms that shape its spiral architecture. The star's properties also provide valuable data on the life cycle of the most luminous, unstable stars. These objects are dynamic, serving as laboratories to understand mass loss, pulsations, and explosive endpoints, supernovae or hypernovae. Observations across different evolutionary stages reveal how such stars shed outer layers, enrich surroundings, and impact future star formation. When a star as massive as Stephenson 2-18 reaches the end of its life, its explosion influences the galaxy environment, triggering or suppressing star formation. Its luminosity and size impact the energy balance within the galaxy. The radiation emitted by Stephenson 2-18 contributes to ionizing surrounding gas, shaping nebulae, and affecting nearby star formation conditions. These luminous giants act as cosmic engines, influencing their environments in various ways. Studying their interactions with surroundings aids astrophysicists in constructing accurate models of the interstellar medium, revealing how energy feedback from massive stars shapes the galactic ecosystem. Additionally, Stevenson 218 serves as a benchmark for calibrating stellar models, especially for the most massive stars. Such models are essential for understanding stellar populations in other galaxies. By analysing this star's mass, radius, temperature, and luminosity, researchers improve theoretical frameworks, helping interpret unresolved stellar populations in distant galaxies. This enhances our understanding of cosmic history, galaxy formation, and large-scale universe structure. The star also refines knowledge of the initial mass function, IMF, which describes the distribution of stellar masses at birth. The upper end of the mass spectrum is extremely rare and difficult to study, but objects like Stephenson 2-18 are vital benchmarks. They inform us about how common or exceptional such stars are, their formation rates compared to smaller stars, and their influence on the galaxy's stellar demographics. These insights are fundamental for modelling the galaxy's formation history and forecasting its future evolution. On a cosmological scale, studying Stephenson 2-18 sheds light on how galaxies are enriched chemically. Massive stars produce heavy elements, carbon, nitrogen, oxygen, and release them during supernovae or stellar winds. These elements seed future stars, planets, and even life. Understanding their life cycle and dispersal mechanisms provides insights into the origin of elements that make up our galaxy and universe. In galactic evolution, Stephenson 2-18 exemplifies the transient nature of massive stars. These stars have short lifespans, burning nuclear fuel rapidly compared to less massive stars. Their brief yet intense existence marks a crucial phase of feedback and transformation. When they explode as supernovae, they redistribute energy and material, influencing galaxy dynamics, chemistry, and star formation. This cyclical process of stellar birth, evolution, and death underpins the ongoing development and reshaping of the Milky Way's structure. Studying stars like Stephenson 2-18 illuminates extreme physical processes operating under conditions unattainable on Earth. Analysing its internal physics, convection, magnetic fields, and nuclear fusion helps scientists understand fundamental laws under extreme environments. These insights contribute to broader fields like plasma physics, nuclear physics, and gravitational wave astronomy. The star also holds importance for future observations and technological progress. Upcoming telescopes, equipped with advanced infrared and high-resolution imaging, will scrutinise Stephenson 2-18 in unprecedented detail. This research will refine our understanding of such stars, star formation, stellar winds, and explosive endpoints. Each discovery advances our models of the galaxy and others, enhancing our grasp of fundamental astrophysical processes. In essence, Stephenson 2-18 is more than a massive star shining at galaxy's edge. It's a crucial puzzle piece, integral to understanding the grand story of the Milky Way. Its properties hold keys to understanding the environments that birth the universe's most magnificent stars, revealing the interconnected physical processes driving galactic evolution. Every insight from this star enriches our knowledge of galaxy growth, change, and the diverse stellar populations illuminating the cosmos. Far from a curiosity, Stephenson 2-18 embodies the dynamic, evolving heart of our galaxy's story, testament to the power and complexity of the universe's stellar engines. Large stars like Stephenson 2-18 are magnificent celestial giants, but they are also powerful agents of change. They shape their environments and influence the galaxies they inhabit, impacting processes from their immediate neighbourhoods to the broader galactic ecosystem. Their influence is fundamental to the life cycle of matter in the universe. One primary way large stars affect their surroundings is through their intense stellar winds, streams of charged particles propelled outward at thousands of kilometers per second. These winds originate from the star's immense luminosity and radiation pressure. As the star exhausts its fuel, its outer layers become unstable, creating a relentless flow of particles that carve out cavities in the interstellar medium. These stellar wind bubbles can stretch across dozens or hundreds of light years, clearing out gas and dust. This process not only sculpts the local interstellar environment, but also triggers secondary effects, compressing nearby clouds, inducing star formation, or dispersing potential stellar nurseries, thereby halting new star births. The interaction between stellar winds and the interstellar medium ISM produces complex multi-layered structures. When the fast-moving winds collide with slower, denser gas clouds, shock waves form, heating the gas to millions of degrees and emitting energetic radiation observable across the spectrum, from X-ray to radio wavelengths. These shock fronts serve as natural laboratories for high-energy astrophysics, revealing details about plasma physics and magnetic fields under extreme conditions. As large stars approach the end of their lives, they often undergo violent supernova explosions, cataclysmic events that release vast amounts of energy, temporarily outshining entire galaxies. The supernova blast propagates outward, sweeping up surrounding gas and dust, forming remnants such as supernova remnants. These remnants are essentially cosmic autopsies, providing clues about the star's final moments and the physics of stellar death. The shockwaves from supernovae heat surrounding media to over millions of degrees, further stirring the galactic environment. Supernova explosions have profound chemical implications. Large stars forge heavy elements, carbon, oxygen, silicon, iron during their lifetimes, and supernovae disseminate these elements into the surroundings. This process, known as nucleosynthesis, enriches the ISM, providing raw materials for future stars and planets. Without such enrichment, the universe's capacity to develop complex molecules, planets, and life would be severely limited. Supernova shocks also contribute to galactic ecology by inducing turbulence in the ISM. This turbulence stirs interstellar gas, raising densities in some regions and lowering them in others, thus influencing star formation rates. Such dynamic processes ensure that galaxies are not static. Instead, they are active, living entities where feedback from massive stars regulates star formation. In regions abundant with such stars, a cycle of formation, evolution, and death creates a feedback loop, shaping the galaxy's morphology and star-forming history. Massive stars influence large-scale galaxy structure and dynamics via their energetic outputs. Their intense radiation ionizes vast areas of gas, creating glowing nebulae called H2 regions. These luminous clouds serve as stellar nurseries where new stars form. Radiation pressure and photoionization can clear out gas, thereby regulating star formation rates. This self-regulation prevents galaxies from converting all their gas into stars too rapidly, helping maintain long-term galactic stability. On a larger scale, the collective feedback from many massive stars, through winds, radiation, and supernova, drives galactic winds and outflows. These phenomena can expel gas from the galactic disk, regulating the galaxy's gas reservoir. Such outflows are crucial for galaxy evolution. They influence chemical enrichment, star formation histories, and black hole growth at centers. Powerful enough, these winds can strip entire galaxies of gas, quenching star formation and changing galaxy morphology over cosmic time. The influence of large stars extends beyond their host galaxies, shaping the universe's overall composition and dynamics. Feedback processes can alter the density profiles and stability of galactic disks, preventing excessive gas clumping. They induce turbulence that maintains a dynamic equilibrium, supporting galactic structures. These mechanisms explain observed galaxy properties, such as star formation rates and chemical abundances, matching theoretical predictions. Large stars are central to cosmic chemical evolution. The heavy elements they produce are incorporated into new stars, planetary systems, and even life. This recycling highlights their critical role in transforming the universe from a primordial mix of hydrogen and helium into the rich cosmos we observe today. In addition, large stars influence the intergalactic environment. Their supernovae and winds can drive material beyond their host galaxy, seeding the intergalactic medium with metals and energy. These outflows impact galaxy formation and structure formation on vast scales, contributing to the cosmic web. Dispersal of enriched gas affects the formation of new galaxies and the evolution of the universe's large-scale structure. Their energetic processes sculpt the grand architecture of the universe, carving out nebulae, enriching media, and regulating star formation. They foster environments of constant change, renewal, and evolution, ensuring the universe remains dynamic. The life cycles of massive stars act as cosmic architects, shaping nebulae, influencing galactic structure, and contributing to the universe's ongoing transformation. Stevenson 218, with its enormous size and luminosity, exemplifies the profound influence such stars wield. They are vital engines of cosmic evolution, their energies and materials echoing across space and time. Their processes create a universe of perpetual motion, where matter is constantly recycled, reformed, and redistributed through stellar life cycles. Their impact extends from the microphysics of shock fronts to the vast scales of galactic and intergalactic structures, underscoring their importance as catalysts of cosmic change. In essence, large stars are the universe's master builders, driving the evolution of galaxies, enriching the cosmos with elements, and inspiring the ongoing story of cosmic transformation. Stephenson 2-18, notable for its size and luminosity, offers insights into star formation, especially in starburst regions. These regions, characterized by rapid star creation, serve as cosmic laboratories for observing massive starbirth and evolution. Studying objects like Stephenson 2-18 aids astronomers in understanding the complex processes governing star formation rates in energetic environments. Starburst regions are often located in merging galaxy cores or areas with interaction funneling gas and dust into dense zones. These regions, rich in molecular clouds, cold, dense gas and dust aggregations, serve as stellar nurseries. Massive stars like Stephenson 2-18 form within these clouds through gravitational collapse of dense cores. Their enormous size, luminosity, and short lifespans make them key indicators of recent star formation activity. Stephenson 2-18's status as an evolved yet relatively young massive star indicates recent efficient star formation. Its existence suggests the region experienced a burst of star formation within the last few million years, producing such colossal stars in a brief period. Analysing its properties, mass, age, surrounding stellar population, helps estimate the recent star formation rate in its host area. Massive stars serve as instantaneous traces of star formation because they live only a few million years, a cosmic blink. The presence of Stephenson 2-18 implies a recent starburst. By examining the number and types of massive stars in a region, astronomers can back-calculate the star formation rate, providing a snapshot of current activity. Because Stephenson 2-18 is highly luminous in infrared and other wavelengths, it allows astronomers to see through dense interstellar dust that would otherwise obscure young stars. Infrared observations penetrate dust clouds, revealing luminous stars hidden in optical wavelengths. Such stars are excellent beacons for gauging star-forming activity within dusty molecular clouds. Constructing a census of massive stars like Stephenson 2-18 enhances understanding of recent star formation activity. The number of such luminous stars correlates with the star formation rate. A higher count suggests a more vigorous starburst, often triggered by galactic collisions or interactions that increase gas density and induce star formation. Stephenson 2-18 also indicates star formation efficiency, the proportion of gas converted into stars within regions. Its properties reveal how effectively gas turns into massive stars, influencing galactic evolution. This efficiency affects feedback processes like stellar winds, supernovae, and radiation, which can regulate or inhibit further star formation. These massive stars exert significant environmental influence through intense radiation and stellar winds, shaping the interstellar medium. Their feedback can spark additional star formation or disperse molecular clouds, halting local processes. Studying Stephenson 2-18 and surrounding regions provides insights into feedback mechanisms that govern star formation rates. Understanding the link between Stephenson 2-18 and the initial mass function, IMF, the distribution of stellar masses at birth, is crucial. Massive stars, though rare, dominate a region's luminosity and energy output. Stephenson 2-18 exemplifies the upper end of this distribution. Its properties can reveal whether starburst environments produce more giant stars compared to calmer regions. The life cycle of stars like Stephenson 2-18 connects to galactic evolution. These stars will eventually explode as supernovae, dispersing heavy elements, metals, essential for planet formation and life. Their supernovae enrich the galaxy chemically, influencing subsequent star and planetary formation. Understanding their formation frequency helps gauge a galaxy's chemical evolution pace. Galactic feedback processes are significantly driven by massive stars in starburst regions. Their energetic outputs, radiation, winds, supernovae, either suppress or stimulate further star formation. Studying Stephenson 2-18 enhances models of these effects, helping us understand galaxy evolution over cosmic timescales. Observations of stars like Stephenson 2-18 across environments refine models of star formation under varying conditions such as low metallicity dwarf galaxies versus metal-rich starbursts. These models are vital for applying local observations to the broader universe and understanding star formation in diverse contexts. Studying objects like Stephenson 2-18 offers clues about early universe starbursts. Evidence suggests early galaxies experienced intense bursts, forming supermassive stars at higher rates. Recognizing how such giants form today helps understand the emergence of the first massive stars and galaxies from primordial conditions. The properties of Stephenson 2-18 and related objects can be analyzed through multi-wavelength surveys, infrared, radio, X-ray, allowing a detailed picture of starburst activity. Stephenson 2-18 serves as a reference point, aiding in calibration of other star formation indicators like radio emissions from HI regions. Furthermore, understanding the life cycle of stars like Stephenson 2-18 within their environments informs feedback loops that influence star formation rates. The interaction between the formation of giant stars, their energetic outputs, and the surrounding medium ultimately shapes galaxy evolution, mass assembly, and morphology. In summary, Stephenson 2-18 is not merely a massive star but a vital probe into star formation in dynamic regions. Its presence indicates recent intense activity and provides a means to quantify galaxy growth and evolution. Studying its properties helps unravel the complex physics governing stellar and galactic development, enriching our understanding of the cosmos. Its study reveals how giant stars form, evolve, and impact their environments, contributing to feedback processes essential for regulating star formation. This in turn influences galaxy structure and chemical enrichment over cosmic timescales. Such insights are crucial for understanding galaxy evolution, star formation history, and matter's life cycle in the universe. Additionally, objects like Stephenson 2-18 serve as benchmarks for testing star formation models across different environments and epochs. Their properties inform theories about how the initial mass function might vary under extreme conditions, impacting our understanding of stellar populations in diverse galactic contexts. Their significance extends to interpreting distant early universe galaxies, where extreme starburst conditions likely produce similarly massive stars at faster rates. Studying present-day analogues offers clues about the processes that led to the formation of the first generations of supermassive stars, shaping the early universe's structure. The connection between Stephenson 2-18 and star formation rates can be exploited through multi-wavelength data. Combining infrared, radio, and X-ray observations produces a comprehensive view, with Stephenson 2-18 anchoring these datasets and serving as a standard candle to calibrate other indicators of star formation. Finally, understanding the life cycle of objects like Stephenson 2-18 within their host environments illuminates the feedback mechanisms controlling star formation. The interaction of massive star feedback with the interstellar medium regulates future star-forming activity, influencing galaxy growth and morphology over billions of years. In essence, Stephenson 2-18 remains a key observational target, providing a window into the processes that drive star formation in the universe's most energetic regions. Its study continues to elucidate the physics of how stars and galaxies form, evolve, and enrich the cosmos with elements necessary for planets and life. Studying extreme stars such as Stephenson 2-18 offers insight into fundamental processes that have shaped our universe over billions of years. These luminous giants are not only fascinating objects, but serve as cosmic laboratories that inform us about stellar life cycle, galactic chemical evolution, and the mechanisms underlying the universe's grand tapestry. Each discovery from these stellar titans helps puzzle together how the universe transformed from a hot, dense primordial state into the vast, complex cosmos filled with galaxies, stars, planets, and life. One key contribution of Stephenson 2-18 to our understanding of cosmic evolution is in advancing stellar physics. As one of the largest, most luminous stars observed, it challenges existing models of star formation, growth, and death. These stars sit at the extreme end of stellar mass, sometimes exceeding 200 solar masses. Such immense mass influences their internal processes, fusion rates, energy output, in ways smaller stars do not exhibit. Studying their structure through spectroscopy and interferometry helps refine theories about energy transport, convection, and core fusion under conditions of intense gravity and temperature. Furthermore, Stevenson 218's size and brightness make it an ideal candidate for testing stellar evolution models. Unlike smaller stars with predictable lifespans, these massive stars undergo tumultuous evolutionary phases marked by rapid change. They shed large parts of their outer layers via intense stellar winds, enriching their surroundings with newly formed elements. Observing these processes in real time allows astrophysicists to better understand how massive stars evolve from main sequence giants through supergiant stages and how they ultimately die. This understanding sheds light on a crucial epoch, the era of element creation and distribution. When massive stars like Stephenson 218 reach the end of their lives, they often explode as supernova, dispersing heavy elements such as carbon, nitrogen, oxygen, and metals into space. These elements are fundamental building blocks for planets, life, and future stars. By studying the life cycles of these massive stars, scientists gain insights into how the universe became chemically enriched. This process influences galaxy formation and evolution, since the ingredients for new star and planetary system formation depend heavily on the distribution of these elements. In addition, studying stars like Stephenson 2-18 illuminates interactions between stellar activity and galactic evolution. Massive stars impact their surroundings through stellar winds, radiation, and supernova explosions, carving cavities in interstellar clouds or triggering new star formation, sometimes inhibiting it by dispersing gas needed for starbirth. Observing and modelling such interactions helps astrophysicists understand how galaxies grow and evolve. These stars act as catalysts, shaping a galaxy's structure and chemical makeup over cosmic time. Examining the life cycle of such colossal stars also enhances understanding of the origins of exotic objects, such as black holes and neutron stars. The mass and evolution of Stephenson 2-18 can reveal clues about the remnants they produce. Some massive stars are believed to collapse into black holes, objects with gravitational pulls so strong that not even light can escape. Studying stars like Stephenson 2-18 improves comprehension of the conditions leading to their formation, core collapse processes, and related phenomena like gravitational waves from black hole mergers. This information is vital for understanding the formation and evolution of complex objects, which are among the universe's most energetic phenomena. Understanding such stars' life cycles also aids the interpretation of distant galaxies. When telescopes look back billions of years in time, the galaxies they observe likely had more massive stars like Stephenson 2-18 due to higher star formation rates. The spectral signatures and luminosities of these ancient galaxies are heavily influenced by their populations of massive stars. Developing detailed models based on stars like Stephenson 2-18 helps astronomers estimate ages, compositions, and star formation histories of distant galaxies. This aids in reconstructing cosmic evolution, how galaxies assembled, grew, and transformed over the universe's history. Beyond astronomy, studying extreme stars drives technological and philosophical advancements, pushing the limits of observational techniques, infrared astronomy, interferometry, spectroscopy, spur innovation in instrumentation and data analysis. These developments often benefit other areas such as medical imaging, telecommunications, and climate science. Philosophically, understanding the life and death of the universe's most massive stars addresses fundamental questions about origins and fate. It prompts inquiries like, how did the universe begin? What is its ultimate future? Could phenomena governed by laws of physics arise in extreme environments that challenge current theories? The existence of such colossal stars also indicates the environments necessary for their formation, informing models of galaxy formation and early universe conditions. These insights help locate potential birthplaces of extreme stars in primordial epochs, when the first galaxies formed from gas. This knowledge adds depth to understanding how the universe's earliest structures emerge from darkness, leading to the rich, organized cosmos observed today. Studying stars like Stephenson 2-18 fosters appreciation for the dynamic cosmos. It reveals a universe of extremes, sizes, energies, and processes governed by the same physical laws as on Earth, but manifesting on incomprehensibly vast scales. Recognizing that humans can understand and explore these giants fuels curiosity, inspiring future scientists, engineers, and explorers to probe the universe's profound mysteries. Ultimately, each discovery about these stellar giants tightens the links between astrophysics, cosmology, and planetary science, creating a comprehensive narrative of the universe's evolution. Lessons from Stevenson 2-18 ripple outward, helping us understand how the universe transitioned from simple, uniform beginnings to the complex structures, galaxies, stars, planets that populate it today. These insights connect the tiniest particles to the grandest cosmic structures, illustrating that the universe's history is inscribed in the life cycles of its most extreme stars. Delving into the fiery cores of objects like Stephenson, 2-18 uncovers cosmic history's secrets. These stars serve as touchstones, revealing the processes that shape the universe. They help us understand our origins and the broader story of existence. It's not just about understanding stars, but about grasping our place in a universe driven by the relentless dance of stellar birth, life, and death, shaping everything we see and know. As we peer into the cosmos, unveiling the secrets of supergiant stars like Stephenson 2-18 becomes an increasingly ambitious quest. The universe doesn't readily reveal its treasures, especially those shrouded in dust, emitting mostly in infrared, or located many thousands or millions of light years away. To understand these colossal objects, astronomers continually push technological boundaries, developing new tools and methods for unprecedented clarity and detail. These advancements are transforming our capacity to observe, analyze, and interpret the life cycles of supergiant stars. One pivotal advancement is infrared astronomy. Traditional optical telescopes often struggle with cosmic dust clouds that scatter or absorb visible light. Supergiants like Stevenson 2-18 are often cloaked in dust, making them nearly invisible in optical wavelengths. Infrared telescopes with longer wavelengths less affected by dust penetrate these shrouds. Ground-based telescopes with sensitive infrared detectors, such as those at the European Southern Observatory in Chile or Hawaii's Infrared Telescope Facility, have revolutionized our study of these stars. The upcoming James Webb Space Telescope, JWST, will take this further, observing in the mid-infrared range. Its high sensitivity and resolution will enable us to peer into previously obscured regions, resolve dusty envelopes, and measure sizes, temperatures, and luminosities of supergiants across the universe. Complementing infrared observations, interferometry has become invaluable. By combining signals from multiple telescopes, astronomers create a virtual telescope with an effective diameter equal to the maximum separation between the instruments. This dramatically increases resolution, allowing astronomers to see features on the surface of supergiant stars that are otherwise unresolved. Optical and infrared interferometers like the Very Large Telescope Interferometer, VLTI, in Chile, or the Center for High Angular Resolution Astronomy, CHARA, array in Georgia, measure stellar diameters, surface features, and atmospheric layers of nearby supergiants. Advances aim to extend these capabilities, enabling detailed surface mapping of stars hundreds of thousands of light years away. Adaptive optics. Technology is another game changer. By compensating in real time for Earth's atmospheric turbulence, adaptive optics sharply images from the ground, approaching the diffraction limit of the telescope. This enhancement allows resolution of intricate structures on supergiant stars and their atmospheres with greater clarity. When coupled with infrared detectors, adaptive optics opens a window into stellar dynamics, surface phenomena, convection cells, pulsations, and mass loss processes, providing deeper insights into their complex behaviors. Spectroscopy has also transformed stellar physics. High-resolution spectrographs on both space and ground telescopes analyze the chemical compositions, velocities, and magnetic fields of supergiants. Advances in sensitivity and stability have enabled detection of subtle spectral line shifts, indicating complex motions and stellar winds. Future instruments, such as the planned spectrographs on the Extremely Large Telescope, ELT, will offer even finer detail. This will enable investigation into the innermost regions of supergiant atmospheres and the mechanisms behind their mass loss phenomena, deepening understanding of their evolution. In addition, computational modeling and data analysis are essential. The influx of high-resolution data demands powerful algorithms for reduction, image reconstruction and interpretation. Machine learning and artificial intelligence are increasingly used to identify patterns, forecast stellar behaviors, and simulate complex stellar atmospheres. These tools help disentangle multi-layered stellar processes, leading to more accurate models and insights into supergiant evolution. The potential of land multi-messenger astronomy also offers promise. Although more established for gravitational waves and neutrino observations of cataclysmic events like supernovae, future developments could detect neutrinos or gravitational waves emitted during massive stars' final stages. Such signals could directly probe core collapse events, complement electromagnetic observations, and provide a more comprehensive picture of supergiant life cycles. Emerging space observatories dedicated to high-energy phenomena will also contribute. X-ray and gamma-ray telescopes observe energetic processes such as stellar winds or supernova remnants. Detecting and analysing high-energy emissions help clarify magnetic fields, particle acceleration, and energetic interactions influencing supergiant evolution, particularly in late stages or during energetic events. Next-generation telescopes like the KIR Extremely Large Telescope, ELTICTUSA in Chile, and the 30-meter telescope, TMTAS in Hawaii, will dramatically push observational limits. With mirrors exceeding 30 meters, these giants will provide unmatched light-gathering power and resolution. They will enable detailed studies of supergiants in distant galaxies, observing surface compositions, pulsation modes, and mass loss events under various galactic conditions. This will shed light on how environmental factors influence their evolution, offering comparisons across cosmic times. Technological advances in detector technologies are also critical. Quantum detectors, transition edge sensors, and superconducting detectors offer higher sensitivity, lower noise, and faster readout speeds. These improvements allow capturing faint signals from dust-enshrouded or distant supergiants, expanding observational dynamic range. The ability to simultaneously examine bright and faint features advances our understanding of stellar structures and processes. These innovations not only improve images or spectra, but fundamentally transform our understanding of supergiant physics. Enhanced resolution reveals surface granulation, pulsation patterns, and mass outflows in exquisite detail, while better sensitivity detects subtle variations over time, refining the timeline of evolutionary stages. Improved models, grounded in rich data, will become more accurate and predictive, advancing interpretations of their life cycles. The integration of multi-wavelength data, from radio and infrared to ultraviolet and X-ray, enables comprehensive portraits of supergiants. Each spectral window highlights different phenomena: cool molecular layers, energetic winds, magnetic activity, or remnants of supernovae. Seamless combination of these observations with sophisticated analysis techniques deepens insights into complex processes and allows us to understand their evolution in context. These technological advances do more than enhance observation. They open new avenues for discovery, challenge existing theories, and inspire new questions about the universe's most massive stars. Each breakthrough brings us closer to understanding how supergiants form, evolve, and end their lives, shaping galaxies, seeding heavy elements, and fueling cosmic cycles. The future of stellar observation is vibrant, driven by rapid technological progress, promising to illuminate the grand tapestry of stellar evolution in ways as awe-inspiring as the stars themselves. Upcoming space missions and ground-based observatories are poised to revolutionize our understanding of colossal stars like Stevenson 218, leading astrophysics into a new era with enhanced insights into their life cycles, internal structures, and ultimate fates. Next-generation space telescopes equipped with advanced infrared and ultraviolet instruments are central to this progress. Missions such as the James Webb Space Telescope, sensitive in the infrared spectrum, can peer through dust clouds that often hide red supergiants like Stephenson 218. Infrared light penetrates these veils, allowing detailed images and spectra of the star's surface and environment. This will enable scientists to monitor atmospheric changes, measure surface temperatures with precision, and analyze the composition of ejected material. These observations will refine measurements of stellar radii and luminosities, crucial for testing stellar evolution models. Stevenson 218's enormous size challenges existing theories. Better data will clarify physical processes regulating such massive stars. For instance, Higher resolution might reveal surface phenomena like convection cells or magnetic activity, influencing mass loss and atmospheric dynamics. Understanding these processes helps predict how stars like Stephenson 218 shed mass and approach supernova explosions. Ground-based observatories, equipped with adaptive optics and interferometry, will complement space-based data. Extremely large telescopes, ELTs, such as the European Southern Observatory's ELT and the 30-meter telescope, will use adaptive optics to correct atmospheric distortions, producing images with clarity comparable to space telescopes but with larger light gathering areas. These capabilities allow astronomers to resolve surface features on red supergiants in exquisite detail, even from Earth. Interferometry, which combines multiple telescopes' light, will measure stellar diameters with exceptional accuracy, enabling direct assessments of Stephenson 218's size, its evolutionary stage, how close it is to ending its life, and the structure of its outer layers. Such measurements can reveal size fluctuations over time, providing clues about the star's instability and processes leading to its death. The synergy between space and ground-based platforms will unlock deeper insights. Simultaneous multi-wavelength observations offer comprehensive views of the star's atmosphere and circumstellar environment. Tracking brightness variations, spectral line profiles, and dust formation in real time is vital, because red supergiants are highly variable, driven by convection, pulsations, and episodic mass loss events. Extended monitoring can identify periods of intensified mass loss or surface upheaval, providing clues about physics shaping their destinies. For example, understanding the timing and mechanisms of mass ejections refines models, predicting whether Stephenson 218 might explode as a supernova soon. Advances will also focus on the star's immediate surroundings, mapping dust and gas shells expelled into space. Infrared and radio observatories can chart dust grain distribution and molecular material, key to galactic chemical enrichment. Measuring dust composition and dispersal patterns reveals how massive stars recycle material and influence galactic evolution. Such detailed mapping highlights their role in seeding future star and planetary system formation, emphasizing their significance in the cosmic cycle of matter. Coupling observational data with sophisticated computational models will yield realistic simulations of these stellar giants. High-quality data from upcoming missions serve as benchmarks for models of stellar convection, magnetic fields, rotation, and mass loss under extreme conditions. This synergy clarifies how stars like Stephenson 218 evolve, shed their envelopes, and approach their explosive ends, shedding light on the physics underlying their life cycle. The era of multi-messenger astronomy adds further potential. Although detecting neutrinos or gravitational waves from red supergiants remains challenging, future observatories might change that. As Stephenson 218 nears collapse, it may produce detectable supernovae, releasing neutrinos and gravitational waves. Observing these signals alongside electromagnetic data would create a multidimensional picture of the star's final moments, revealing core collapse physics and explosion mechanisms that are currently poorly understood. Large-scale sky surveys and transient detection facilities will be crucial for early identification of stars like Stephenson 218 before they explode. Rapid alerts will enable coordinated multi-wavelength follow-ups, capturing the last phases of massive stars' lives in detail. Early detection of supernova precursors will deepen our understanding of explosion mechanisms, remnants, and asymmetries, advancing the field significantly. Historically, studying red supergiants has been limited by distance, dust obscuration, and resolution constraints. But technological advances reduce these barriers. Higher spectral resolution instruments will dissect atmospheres and ejected materials' chemical makeup, unveiling ongoing nucleosynthesis within these giants. This contributes essential knowledge about element formation and dispersal, key to understanding cosmic chemical evolution. Looking further ahead, mission concepts like space-based interferometry and ultraviolet telescopes could directly image surface features, sunspots, convection cells, magnetic activity, in remarkable detail, providing intimate views of the forces shaping these stars. Such capabilities would illuminate the complex interactions driving their turbulent lives and eventual deaths, revealing the physics at play in these stellar giants. In essence, the future of massive star research is promising. Each technological advance and observation refines our understanding of their intricate lives. Their enormous sizes and turbulent behaviours serve as cosmic laboratories for extreme physics, stellar evolution, and galactic enrichment. As tools develop, we will not only observe but understand the processes behind their grand finales, uncovering fundamental cosmic mechanisms and broadening our cosmic perspective. This ongoing progress will shed light on key questions about the internal dynamics, mass loss, and end-of-life scenarios of stars like Stephenson 2-18. Unraveling their mysteries enhances our understanding of stellar evolution, heavy element production, and matter's life cycle in the universe. Moreover, future multi-messenger detection, capturing neutrinos, gravitational waves, and electromagnetic signals, will revolutionize our understanding of supernovae and the physics under extreme conditions. Observing a core collapse event in detail would confirm models, reveal asymmetries, and clarify core collapse mechanisms that remain elusive. To summarize, technological advancements will dramatically enhance knowledge of stars like Stevenson 2-18. From resolving surface features to mapping circumstellar material and detecting stellar death signals, each breakthrough tightens the narrative of how these giants live and die. These efforts deepen comprehension of stellar physics, chemical element production, and their roles within the galactic ecosystem, advancing cosmic understanding. The coming decades promise unparalleled insights into these behemoths. As observational tools grow more sophisticated, understanding of their complex life cycles will deepen, illuminating their influence on galaxies, the forging of elements, and their spectacular endings in cosmic light shows. The next era of astrophysics will turn isolated observations into a comprehensive picture. How stars like Stephenson 2-18 shape galaxies, seed future generations of stars, and ultimately end in explosions that light up the universe. Confirming the size and properties of the largest stars like Stephenson 2-18 presents a constellation of formidable challenges that stem from the very nature of these cosmic giants. While advancements in telescopic technology and astronomical techniques have propelled our understanding forward, these colossal stars still pose riddles that scientists are striving to decode. First and foremost, one of the most significant hurdles is their vast distance from Earth. Stephenson 2-18 resides deep within our galaxy, obscured by dense clouds of cosmic dust and gas. These obscuring materials absorb and scatter much of the visible light emitted by the star, rendering traditional optical observations largely ineffective. The star's veiled environment necessitates the use of infrared astronomy, which can penetrate dust more effectively. Even then, the increased wavelength introduces its own complications, such as lower resolution and challenges in accurately pinpointing the star's precise location and size. Building upon that, the enormous size of these stars amplifies the difficulty further. When a star becomes a red supergiant of such immense proportions, it's not just a simple glowing sphere. Instead, it develops an extensive and complex atmosphere with a chaotically turbulent surface. Its outer layers are often warping and expanding at irregular velocities, driven by intense convection currents and radiative pressures. This turbulent atmosphere makes it incredibly challenging to determine a definitive boundary, the so-called photosphere, which is used as a reference point for measuring size. Different methods of measurement might yield varying estimates, sometimes differing by hundreds of solar radii, raising questions about the true scale of these giants. Compounding this issue is the star's variability. Red supergiants are notorious for their fluctuations in brightness and size over periods spanning months to years. These pulsations and convective motions cause their atmospheres to expand and contract, making it difficult to establish a stable measurement. When observing a star that is constantly changing, multiple measurements over time are needed to understand its average properties accurately. Yet, the variability adds uncertainty to measurements, and capturing the precise moments for accurate assessment proves challenging. Another complex aspect is the difficulty in modelling these stars due to their unique physical conditions. Their immense size and mass mean they operate in regimes of stellar physics that are not entirely understood. The internal processes, like nuclear fusion in the core, convection in the outer layers, and mass loss through powerful stellar winds, are all extreme and interlinked. Accurately simulating these processes requires computational models that are immensely sophisticated and resource-intensive. Small errors or assumptions can lead to significant discrepancies between what models predict and what observations reveal, making it hard to confirm their true sizes and properties. Interferometry, a technique that combines light from multiple telescopes, has been instrumental in resolving details of these distant giants. It allows astronomers to achieve a resolution high enough to measure their angular diameter. However, even interferometry faces limitations. The faintness of these stars in the optical and infrared band, combined with the atmospheric interference in Earth's environment, can limit the precision of measurements. Additionally, the interpretation of interferometric data depends heavily on models of stellar atmospheres, which, as discussed, are uncertain for such turbulent and large stars. Distance measurement is yet another significant obstacle. Determining the physical size of a star requires knowing its distance with high precision. For nearby stars, parallax measurements provide reliable distances, but for stars like Stevenson 2-18, their distance is often estimated indirectly through methods like associating them with clusters or using intrinsic brightness assumptions, which can introduce large uncertainties. The errors in distance measurement directly translate into uncertainties in size estimates, because the star's angular diameter, combined with its distance, gives its linear size. Furthermore, the star's environment adds layers of complexity. As a luminous red supergiant, Stephenson 2-18 is likely losing mass through stellar winds, creating a surrounding envelope of gas and dust. This circumstellar material can obscure the star further and interfere with measurements, especially in the infrared and radio wavelengths. Differentiating between the star's actual surface and the surrounding dust shell is a meticulous process that involves modelling the dust distribution, which itself is fraught with uncertainties. Spectroscopic analysis, fundamental for understanding a star's temperature, composition, and velocity, also encounters obstacles when applied to these giants. The dense extended atmospheres produce broad, blended spectral lines, complicating the extraction of precise data. The dynamical motions within the atmosphere cause line shifts and broadening, which can be mistaken for other effects or cause misinterpretation of the star's physical state. The variability, turbulence, and the complex interplay of physical processes also mean that any single observation provides just a snapshot in an ever-changing environment. To truly grasp the properties of such enormous stars, astronomers must piece together a mosaic of data from multiple epochs, wavelengths, and techniques. This comprehensive approach demands significant observational time and resources, all while dealing with the intrinsic limitations of each method. There's also an element of inherent cosmic unpredictability. Despite all our technological advancements, stars remain natural phenomena governed by physics that can still surprise us. Additional complexities, such as magnetic fields, rotation, binary interactions, or episodic mass loss events, can all influence the star's apparent size and properties. These factors add further layers of challenge, because they require more sophisticated models and interpretation. Moreover, the final stages of massive stars, massive red supergiants like Stephenson 2-18, are especially elusive. They are transient on cosmic timescales, undergoing rapid and tumultuous changes that can last mere thousands to tens of thousands of years, a blink of an eye in astronomical terms. This fleeting window makes it difficult to observe their full evolutionary pathways and confirm their extreme properties. In summary, confirming the size and properties of the largest stars like Stephenson 2-18 involves navigating a labyrinth of observational, analytical, and theoretical challenges. The vast distances and dust obscuration require high-tech observational techniques, while their turbulent atmospheres, variability, and complex environments demand sophisticated models and repeated measurements. Despite these hurdles, the progress made underscores the ingenuity of astronomers and the relentless pursuit of understanding these magnificent celestial behemoths. Each challenge surmounted brings us one step closer to unraveling the mysteries of stellar extremes, shedding light on the life cycles of the universe's most massive stars. As we continue revealing the complexities of Stephenson 2-18 and other giant stars, the importance of theoretical modelling and simulation becomes clear. These tools guide us through the uncharted territories unveiled by advanced observations. The rapid influx of data from telescopes and missions can be overwhelming, yet without equally sophisticated theories, our understanding risks falling behind. How can models keep pace with constant observational discoveries? At the heart of this challenge is the dynamic relationship between data and theory. Observations provide snapshots, moments capturing stars like Stephenson 2-18, showing their size, luminosity, temperature, spectral features, and extended atmospheres. These discoveries often reveal phenomena that challenge existing models. For example, Stevenson 218's enormous size, mass loss rates, and circumstellar structure have prompted scientists to refine stellar evolution theories and mass loss mechanisms in massive stars. To stay in sync, theoretical models must become more adaptable and detailed. Multidimensional simulations, especially 3D hydrodynamic models, are essential. Unlike traditional 1D models assuming symmetry, these simulations capture the turbulent surfaces, vigorous convection, and anisotropic mass loss typical of red supergiants like Stephenson 2-18. They allow detailed modelling of convective motions, pulsations, and localised mass ejections. Developing these models isn't just about computational power. It requires incorporating physics at multiple scales, from quantum processes deep within the star to the dynamics of expanding gaseous shells. Advances in computational astrophysics are enabling this progress. High-performance supercomputers can run simulations with billions of grid points, solving equations governing fluid dynamics, radiative transfer, magnetic fields, and nuclear reactions. Such detailed models can generate synthetic spectra and images directly comparable with observations, increasing their robustness and predictive power. In addition, observational feedback is increasingly integrated into modelling efforts. Observations now serve not only as data points, but as constraints shaping models. This iterative process, where simulations predict features, observations seek them out, and surprises lead to model refinement, is vital. Tools like machine learning and Bayesian inference help analyze vast parameter spaces, identifying physically plausible conditions matching observed phenomena. For instance, detailed measurements of Stevenson 2-18's mass loss, temperature variations, and dust shell structures have led theorists to update models of stellar atmospheres, incorporating complex dust physics, radiation hydrodynamic instabilities, and magnetic activity. These refined models help explain episodic mass loss and asymmetric outflows, phenomena previous simpler models couldn't account for. Fostering close collaboration between observers and theorists further accelerates progress. Multidisciplinary teams, comprising observational astronomers, computational astrophysicists, nuclear physicists, and chemists, speed up the cycle of hypothesis, modelling, observation, and revision. For example, if observations reveal a specific chemical signature in Stevenson 2-18's circumstellar material, models can incorporate detailed chemical networks, refining our understanding of surface mixing and wind chemistry. While computational capabilities have grown rapidly, modelling the full life cycle of stars like Stevenson 2-18 remains daunting. These stars evolve over millions of years, with gradual changes. To simulate such timescales, scientists develop sophisticated stellar evolution codes incorporating modules for convection, rotation, magnetic fields, and mass loss. These are often coupled with hydrodynamic models of the star's outer layers and its surroundings. By embedding multidimensional effects into one-dimensional evolutionary models, using parametric modelling or fitting functions, researchers approximate three-dimensional influences without prohibitive costs. Understanding the end stages of massive stars is equally critical. They involve extreme regimes of density, temperature, and quantum physics, requiring integration of nuclear physics simulations with hydrodynamic models. Such models are increasingly tested and refined using observational data, like gravitational waves from supernova remnants or neutrino detections, leading to better accuracy. The rise of machine learning and AI is transforming modelling. Neural networks trained on large datasets from simulations and observations serve as surrogate models, predicting stellar behaviour across wide parameter ranges with remarkable speed. These models often detect subtle dependencies and correlations that traditional analysis might miss, enabling rapid iteration. When combined with real-time observational data from instruments like space telescopes or interferometers, AI-driven models can generate near-instant predictions about stellar states and evolution, guiding observational campaigns and enabling immediate theoretical feedback. Technological advancements further close the gap between observation and simulation. Improved instruments, adaptive optics, interferometers, high-resolution spectrographs produce detailed data on stellar surfaces, atmospheres, and winds. As data fidelity increases, models must incorporate more complex physics to replicate observed phenomena. This dynamic interplay pushes models toward more physically complete representations, reducing reliance on approximations. Open-source modular modelling frameworks are also crucial. Sharing code, physics modules, and simulation results fosters collaboration, accelerates development, and encourages standardization. Comparing models across research groups against consistent observational datasets leads to consensus and continuous refinement. Such collaborative ecosystems help develop versatile models capable of adapting to new discoveries swiftly. Anticipation and flexibility are key. As we find more objects similar to Stevenson 2018, theorists must update models with new physics, refined dust formation, magnetic effects, or rotation impacts. Keeping pace involves not just reacting to data, but proactively developing predictive models. These allow us to anticipate phenomena yet to be observed, guide future observations, and generate testable hypotheses. In sum, to match the rapid flow of observational breakthroughs, theoretical modelling and simulation need to evolve into dynamic, integrated systems. They must embrace multi-scale, multi-physics approaches, leverage artificial intelligence, and be built on open, collaborative platforms. Fostering a close synergy between observation and theory enables models not only to keep pace with discoveries, but to drive deeper understanding of massive stars like Stephenson 2018. This ongoing evolution ensures our theoretical frameworks remain integral to unravelling the secrets of the universe's most luminous giants. The discovery and study of the largest stars in the universe, like Stephenson 2-18, provide crucial insights into the extremes of stellar physics. These colossal giants, with their immense sizes and luminosities, serve as natural laboratories where fundamental laws of physics are tested. Examining such stellar behemoths enhances understanding of the universe's life cycle, composition, and evolution. A key significance lies in understanding stellar formation, growth, and death. Traditional models based on modest-sized stars often fall short in predicting behaviours of supergiants like Stephenson 2-18. Observations reveal that their size, mass, and energy output challenge existing theories, especially regarding stellar winds. Powerful streams of charged particles emitted by these stars. These winds carry away massive amounts of matter, influencing their evolution and ultimate fate. Moreover, these enormous stars have remarkably short lifespans, just a few million years, indicating rapid nuclear fuel consumption. Studying them provides vital clues about early stellar evolution and their contributions to galactic chemical enrichment. When they explode as supernovae, they disperse heavy elements like iron, nickel, and other metals into space. These elements form the raw materials for new stars and planets, including potentially life-bearing worlds. Thus, the fate of big stars directly impacts cosmic chemistry, fostering diversity in planetary systems. Beyond element synthesis, the largest stars are crucial for understanding galaxy evolution. Their extreme brightness enables astronomers to observe them across vast distances, even in dense galaxy centres. Studying these stars helps map star formation activity in various environments and reveals feedback mechanisms between massive stars and their surroundings. Their radiation and stellar winds carve cavities in the interstellar medium, triggering or suppressing subsequent star formation. This dynamic shapes galaxy architecture and evolution over cosmic timescales. The impact of giant stars on their interstellar environment is also significant. Their energy output influences the temperature, pressure, and composition of surrounding gas and dust. Observations help us understand their role as cosmic sculptors, creating nebulae, regulating star formation, and contributing to galactic turbulence. Furthermore, understanding mass loss processes informs models of feedback mechanisms, shedding light on how energy moves through galaxies and affects their structure. Fundamentally, studying the biggest stars advances stellar physics by challenging and refining theories. Many display behaviours perplexing scientists, prompting the development of new models or revisions. Their complex atmospheres and variable luminosities necessitate sophisticated understanding of stellar atmospheres, convection, and radiation transfer. These efforts deepen our grasp of matter under extreme conditions, high temperatures, densities, and radiation pressures, pushing physics to its limits. The quest to understand these stars also explores the maximum size and mass limits of stellar objects. Is there a size limit before a star becomes unstable or collapses into a black hole or neutron star? Observations of supergiants like Stephenson 2-18 provide data to constrain these limits. Studying such objects helps piece together boundary conditions set by gravity, radiation, and nuclear processes, offering insights into possible final states of the universe's most massive stars. From a cosmological perspective, large stars may serve as distance indicators, aiding measurements of cosmic scales. While not as precise as Cepheids or TP supernovae, their incredible brightness could complement existing methods to probe distant regions of the universe. This can refine understanding of cosmic expansion, matter distribution, and structural evolution on large scales. Technological advances in astronomy are crucial for studying these giants. Detecting and analysing distant luminous stars depends on cutting-edge telescopes, spectrometers, and imaging techniques, such as infrared observations that pierce through dust. Improved technology enables astronomers to discover even larger, more massive stars, continually pushing astrophysical frontiers. This progress enhances models and deepens comprehension of these stellar giants' roles in cosmic phenomena. Culturally and philosophically, the discovery of the universe's largest stars symbolises the grandeur and complexity of the cosmos. These stellar giants inspire awe, fueling human curiosity and the desire for understanding. Their existence beyond our reach fosters humility and encourages exploration. Recognizing such colossal objects reminds us of the universe's vastness and our place within it, inspiring ongoing discovery and wonder. In a broader sense, studying these massive stars aligns with humanity's quest to understand origins and our cosmos. Each discovery adds a piece to the grand puzzle, helping assemble a comprehensive picture of cosmic history. These giants are not just astronomical curiosities, but vital threads woven into the story of matter, energy, and life's evolution over billions of years. Investigating stars like Stephenson 2-18 uncovers critical secrets about stellar physics, galaxy dynamics, and cosmic chemistry. Each data point enriches a vast mosaic of knowledge, shaping our understanding of the universe's past, present, and future. These giants are key to unlocking cosmic mysteries, enduring symbols of knowledge-seeking and our unending pursuit to comprehend the universe's awe-inspiring complexity. They help explore limits of stellar stability and collapse. By studying their properties, scientists aim to determine if a maximum size exists before instability or collapse into black holes or neutron stars. This research informs theories about black hole formation and the universe's ultimate fate. Understanding these limits advances knowledge of gravitational physics and nuclear constraints within stars. Furthermore, examining these giants enhances understanding of their influence on galactic ecosystems. Their energetic outputs shape interstellar clouds, influencing star formation rates and patterns. This feedback mechanism is essential for grasping galaxy evolution and matter-energy distribution across the cosmos. Studying massive stars highlights the importance of technological progress. As observational tools improve, astronomers can detect and analyze more distant luminous giants, refining models. Progress in infrared, spectroscopy, and space telescopes like James Webb enables deeper insights into these stars, revealing more about their nature and cosmic roles. Additionally, these discoveries serve as reminders of the universe's wonder and inspire future scientists. They exemplify human curiosity and the drive to explore the unknown, fueling technological advances in scientific inquiry. The study of these stars fosters cultural appreciation for the universe's grandeur, connecting science with philosophy and the human spirit. Overall, investigating the larger stars is fundamental to understanding the universe's physical laws, the life cycle of matter, galaxy formation, and the evolution of cosmic structures. Each insight contributes to a more comprehensive picture, showing how extreme astrophysical phenomena influence the universe's past, present, and future. These stellar giants are not merely objects of interest, but symbols of the enduring human quest to decipher cosmic mysteries. In conclusion, studying enormous stars like Stephenson 2-18 opens a window into extreme physics, galactic processes, and cosmic evolution. They challenge existing theories, aid in understanding the universe's structure, and inspire technological and philosophical growth. These giants are essential to unraveling the universe's past and predicting its future, exemplifying human curiosity and our unending pursuit of knowledge in the grand cosmic story. The discovery of Stephenson 2-18 has significantly advanced our understanding of stellar size limits and extremes. Prior to its identification, astronomers recognized a maximum stellar size based on models and observations of red supergiants like Betelgeuse and VY Canis Majoris. These giants, already colossal compared to our Sun, demonstrated impressive dimensions, but Stephenson 2-18 shattered previous records, prompting a re-evaluation of stellar physics boundaries. What makes Stephenson 2-18 remarkable is its immense volume and mass. With an estimated radius over 2,000 times that of the Sun, it surpasses even the largest known red supergiants. To visualize, if placed in our solar system, it would extend beyond Jupiter's orbit, engulfing Mercury, Venus, Earth, Mars, and reaching into the asteroid belt. This enormous size challenges the limits of star growth before instability or mass loss through stellar winds occurs. The star's size enhances our understanding of physical processes in stellar evolution, especially during late stages of massive stars. The key question is, how do stars attain such size? Conventional models suggest that during the red supergiant phase, stars expand as they exhaust nuclear fuel. However, Stephenson 2-18 indicates models may underestimate maximum sizes, or that additional factors, mass loss rates, metallicity, or magnetic activity, are allowing stars to grow beyond previous estimates. Moreover, Stephenson 2-18 highlights the importance of mass loss mechanisms. As stars expand to such sizes, they shed mass via strong stellar winds, driven by intense radiation and dynamic outer layers. Its characteristics suggest an extraordinary mass loss rate, providing insight into how massive stars disperse material into the interstellar medium. These processes enrich galaxies with heavy elements, enabling new star and planet formation and influencing galactic chemical evolution. The star's size prompts a re-evaluation of the upper mass limit of stars. It was long believed that stars couldn't surpass roughly 150 solar masses because radiation pressure counteracts gravity. Stephenson 2-18 suggests stars might extend beyond this boundary, or that such massive stars exist on a continuum beyond previous limits. This raises questions about their formation. What initial conditions allow their assembly, whether these stars are rare anomalies, or more common but hidden behind dust or too faint at peak size to be easily detected. These considerations reveal that stellar size is dynamic, evolving through complex interactions among gravity, nuclear fusion, mass loss, and environment. The existence of a star like Stephenson 2-18 indicates the upper size limit isn't fixed but is flexible, influenced by initial mass, metallicity, and evolutionary pathways. It demonstrates that under certain conditions, stars can grow to extraordinary sizes before their life cycle culminates in supernovae or other end states. From a broader perspective, Stephenson 2-18 links stellar size with galactic evolution. Such massive stars are rare but highly influential, shaping their environment with intense radiation, winds, and explosive deaths. Their final stages, supernovae or black hole formation, significantly impact surroundings. Understanding these giants clarifies feedback mechanisms regulating star formation in galaxies and their development over cosmic timescales. The star also informs models of stellar stability. Physics constraints, like the Tolman-Oppenheimer-Volkoff limit for neutron stars and bounds set by radiation pressure, define maximum sizes and masses. Discovering Stephenson 2-18 pushes these theories to their limits, hinting at possible pathways to stability previously unimagined. It suggests gravity can, under specific conditions, overcome opacities and winds, enabling extremely large stars. Furthermore, the discovery emphasizes the need to refine observational techniques for such stars. Detecting and measuring stars thousands of light years away is complex, requiring sophisticated infrared telescopes capable of piercing cosmic dust and advanced modeling algorithms. Identifying such giants underscores technological progress and highlights how much remains to be learned. It reveals a frontier in astrophysics challenging existing models and opening doors to discovering even more extreme objects. Stephenson 2-18's existence impacts our understanding of stellar life expectancy. Due to their enormous size, these stars burn through nuclear fuel rapidly, resulting in relatively short lifespans, just a few million years. Their fleeting existence makes them remarkable, requiring rapid assembly of such massive structures before their demise. Studying these stars provides snapshots of dramatic stellar evolution, revealing raw physics at its most extreme. Additionally, Stevenson 218 influences theories of star formation. Its existence suggests initial mass functions, descriptions of star mass distributions at birth, may need adjustment to include such giants. This impacts models of galaxy evolution, the distribution of stellar populations, and the universe's chemical enrichment through successive generations of stars. The presence of such giants indicates that upper ends of these functions are perhaps more variable and extensive than previously thought. Ultimately, the star challenges notions of what is possible in the universe. It exemplifies how the cosmos can produce objects that stretch the limits of current understanding. Continued observation and analysis of Stephenson 218 serve as reminders that the universe is a dynamic laboratory of extremes, and that discoveries like this push the boundaries of knowledge. They motivate ongoing research and inspire new questions about formation, stability, and evolution of the most massive stars. Its existence spells a need to refine models of stellar physics, especially regarding stability limits and mass loss processes. It underscores that physics constraints are not absolute, but are dependent on context, with certain conditions enabling stars to reach sizes and masses once thought impossible. Studying Stephenson 218 helps uncover alternative pathways of stellar growth and death, enriching our understanding of stellar physics. This discovery emphasizes the importance of advancing observational technology, particularly infrared astronomy, capable of probing dusty regions where such giants often reside. The more we learn about Stephenson 218, the more we realize how much remains undiscovered. It invites a reassessment of how many such stars might exist but remain hidden, challenging us to develop more sensitive instruments and techniques. Finally, Stephenson 218 serves as a reminder of the universe's diversity and capacity for extremes. Its existence invites awe and curiosity, exemplifying that the universe's potential is still unfolding. As we continue to study these massive stars, we deepen our understanding of stellar and galactic evolution, inspiring the pursuit of knowledge about the vast, extraordinary cosmos. Understanding colossal celestial objects like Stephenson 218 broadens our minds and shifts perspectives profoundly. These giants aren't just massive stars by cosmic standards. They serve as gateways to contemplating our universe's origins, mechanics, and existence itself. From a scientific viewpoint, their implications are monumental. Studying stars like Stephenson 218 advances astrophysics, stellar evolution theories, and the physics of matter under extreme conditions. These giants challenge models, reshaping them. Traditional theories about star formation, lifespan, and death are tested by such titanic entities. Their size, luminosity, and life cycles expose gaps in understanding, prompting refinements in equations and the development of new theories about their formation, stability, and fate. Examining their interiors provides insights into matter under densities and temperatures far beyond Earth's capabilities. How does a star maintain stability despite such enormous gravity? What roles do radiation pressure and convection play in energy balance? These questions deepen our grasp of nuclear physics, plasma behavior, and the forces governing the cosmos. Each observation opens new avenues of knowledge, bringing us closer to a unified understanding of fundamental laws. On a broader scientific level, these stars act as natural laboratories for understanding matter's life cycle in the universe. They offer clues about element formation in massive star cores and their dispersal via supernova or stellar winds. This material contributes to planetary formation and life's emergence. Deciphering their internal processes reveals cosmic cycles of matter, demonstrating how the universe continuously recycles itself. Philosophically, contemplating such colossal stars confronts ideas of scale, insignificance, and interconnectedness. These giants, many thousands of times larger than the Sun, dwarf human existence and our fleeting moment in cosmic history. Their existence prompts reflection on our place in the universe, not as dominant beings but as tiny sparks in a vast cosmic story. They foster humility needed to comprehend such grandeur and emphasize curiosity and exploration. Peering into space and discovering these titans encourages reconsideration of notions of significance and the limits of understanding. These stars inspire philosophical debates about reality, infinity, and origins. The universe's ability to produce such complex objects suggests principles that are elegant yet intricate. Questions arise. Why does the universe allow stars of this magnitude? What do they reveal about the cosmic fabric? It's harmony or chaos? Are these stars anomalies or essential to cosmic evolution? Their immense scale and mysteries challenge us to reflect on the universe's purpose and whether it has one. Studying these giants fosters a sense of interconnectedness. Every atom in Stevenson 2-18 was forged in previous generations of stars, tying its existence to cosmic history spanning billions of years. Understanding each phase of its life cycle enhances our appreciation for the resilience and continuity of matter and energy over time and space. It underscores how all things, from particles to stars, are woven into the fabric of space-time. The abundance of such stars prompts existential questions about our future and the universe's destiny. Could stars like Stephenson 2-18 explode as supernovae or collapse into black holes, unleashing radiation and matter? If so, how might these events influence planetary systems, including ours? Such considerations highlight the transient nature of everything and inspire wonder and responsibility to safeguard our planet amid the universe's vastness and change. The discovery and ongoing study of stars like Stephenson 2-18 influence perspectives on technological progress and human ingenuity. Observing these objects requires advanced tools, adaptive optics, infrared telescopes, sophisticated models. These efforts exemplify human curiosity and our capacity to extend senses beyond terrestrial limits. Analyzing their complexities demonstrates technology's power to expand knowledge, foster exploration, and inspire innovation. Embracing such objects challenges us to think big and imagine possibilities beyond immediate experience. Realizing the universe can produce stars thousands of times larger than our Sun inspires awe, revealing a cosmos far more astonishing than everyday perceptions. This fuels discovery, motivating future generations to question deeply and push beyond current limits. Considering their life cycle, birth amid nebulae, exponential growth, eventual demise, mirrors themes of growth, transformation, and renewal. Just as stars form, evolve, and fade or explode, so do phenomena in life, history, and knowledge. Their existence acts as a cosmic metaphor for impermanence, change, and the universe's dynamic nature. Recognizing these patterns encourages acceptance of change, curiosity, and finding meaning in becoming. The extremities of objects like Stephenson 2-18 also challenge notions of nature's limits. Previously, stars were thought to have upper bounds in size and mass, yet these giants defy those limits, suggesting the universe is more inventive and less constrained. This knowledge fosters philosophical humility, reminding us that understanding evolves and that the universe may hold secrets beyond our wildest conceptions. The recognition that physical and mathematical boundaries are tested prompts debate about human knowledge's scope. Are there ultimate laws governing the universe, or is reality an endless landscape of possibilities? The existence of such stars fuels ongoing scientific and philosophical inquiries into the universe's origins, fate, and existence itself. Ultimately, understanding objects like Stephenson 2-18 presents a universe that is humbling yet exhilarating. It reminds us of our place in an